All right. Welcome back, everybody, to QHack. This is the first day of a very jam-packed couple of days from talks from all of our sponsors, which I will show you on the screen right now. Thank you to all of our sponsors. Really appreciate all that you do for QHack. Without you, we wouldn't be able to do this event. So thank you very, very much. We do appreciate that. I'll throw the schedule up on the screen right now, but if you do have any questions or concerns or want to see more information about today's agenda, please go to qhack.ai. I think our mods will put a link in the chat to the schedule for the stream today and tomorrow. We'll be hearing from our sponsors. All right, so our very first guest is Willem from TNO. Willem is a scientist and innovator at the Netherlands Organization for Applied Research, which is a partner of the Quantum Application Lab. He's a member of the Department of Applied Cryptography and Quantum Applications. Willem, welcome. It's great to have you today. How are you doing?
I'm doing great. Yes.
Awesome. All right. Well, the floor is yours for QGIM. So we'd love to hear more about that. Take it away. The floor is yours.
Well, thank you. Also, thank you, QHack, for the opportunity to tell something about QGIM. Yeah, it's a great opportunity to share something about what reinforcement learning can mean to the world of quantum computers. And today I will show you a bit about what we have built. It's the QGIM, and it's a GIM to train and benchmark reinforcement learning based quantum compilation. I do this together with Sebastian Veld, who is a professor at the TU in Delft, which is a technical university in the Netherlands. And with my colleague Stan and former colleague Tarik, we built this GIM. And QTech, who is the owner of this GIM, is a collaboration between the Technical University in Delft and TNO. TNO is the Applied Research Institute of the Netherlands. Okay, so what will I be talking about? First, I will give a bit of a background, both of what reinforcement learning is about, and also how can you look at the compiler. And then this will be the stepping stone for telling about how you can combine these two subjects. Then I will share something about the goal of why we built the GIM at first, and now also about how it is developing. I will give a short overview of how the GIM is structured and how you could work with it. And before wrapping it up, I will show an example of how you can apply reinforcement learning to the act of routing. And there I will also highlight a bit of how people can play with our GIM to see how they can improve the compilation. And we will wrap up with what's ahead. Okay, so let's start. What is a quantum compiler? Basically, we all know what a quantum circuit is. It's just the qubits with the gates and operations between gates. And somehow you want to run this circuit on quantum hardware. And the quantum hardware can vary a lot in terms of topologies, in terms of fidelities, in terms of operation times, and really hardware specific things. So the generic quantum circuit always needs something in between, which is the quantum compiler. And basically every computer or many things in the world have a compiler to go from the generic case to the specific implementation, and the quantum computer also has this. And our goal with the QGIM is to improve this bridge. If you look inside a quantum compiler, you can see it as a set of passes or a set of functionalities. And a compiler always has a set of functionalities which it has to apply before the compilation is ready to execute some code on the actual device. And some of these passes are easy. If you have a certain gate, I think this is a C0, and then you need to compose them such that they can be decomposed into the native gate set of the actual device. This is a really straightforward task, and this can be done once the native gate set is known, and how to convert every gate that's not in a native gate set to this native gate set. However, there are also some passes that are really difficult. And one of these things is the initial mapping. So this means if you have the logical qubits in your quantum circuit and you want to map them onto quantum hardware, you need to choose which logical qubit in your circuit will correspond to what physical qubit in your quantum hardware. And the problem itself seems really easy, but to do this in an optimal way is really hard. And the mapping also really implies a lot for how the routing has to be done and how all the operations on the device have to be scheduled. So this problem is NP hard, and therefore it's really suitable to try different methods to solve this, because NP hard problems are not solvable in polynomial time. So either if you want to solve this problem, you need some heuristics or some other methods to do it. Well, what do we then focus on? So we focus at this moment on three passes, namely the mapping pass, the scheduling pass, and the routing pass. And we try to improve these difficult passes with reinforcement learning. So what then is reinforcement learning? Okay, so imagine you have a maze, which we call the environment, and you have a software agent, which is this nice emoticon on the slide. And an agent can observe something. For example, the agent says, I observe one wall behind me and the other spaces are free. So on the left, on the right, and up, the spaces are free. And the agent has to decide what to do. And we say that the goal for this agent in this example will be to find a way out of the maze. And it does this by observing, then taking an action, and every time it has done an action, it will get some kind of a reward, or maybe after it has finished the whole process of getting out of the maze, it will get a reward, or you can sometimes also do it step by step. And if you then give an agent a lot of different mazes, and every time you give a certain type of a reward, so if it does it very quickly, you give a good reward. If it does it slow, you give high punishments. Then the agent can learn through this reinforcement process, the process of penalizing and rewarding. It can learn to execute this task. Well, then what is the goal of the quantum compiler or the quantum compilation gym? You can compare it with the human gym. In the human gym, people are pushing heavy weights, doing tough tasks, and sweating to get stronger and to be able to either push heavier weights or push it more often in the same time. And yeah, you could say about being in the gym, it never gets easier, but you just get stronger. And it's also when you are running, they say it never gets easier, but you just go faster. And same holds also for reinforcement learning. The agent will try to learn these tasks, and hopefully it will learn to do it faster than existing heuristics or other types of algorithms. So what does the gym consist of? In a human gym, you have a collection of training equipment, and in the reinforcement learning gym, you have a collection of training environments. And the training equipment in a normal gym is standardized. It's such that people know how to work with it. And that is really accessible for many people. And in the same way, we want to have a standardized API so that it's easy for many people that are developing quantum algorithms or look at the process of quantum compilation, that it's intuitive for them to work with it. Then why do we want the gym? First of all, we want a standardized API. And this had a reason also in the Netherlands within QTech. What happened a lot was that the actual compiler of the device in the Netherlands was written in C++, and the language was not really accessible. It had a lot of internal optimizations, and sometimes people try to extend the compiler by adding some components or functionalities. And by doing so, a lot of researchers, different researchers or developers, got a lot of incompatible compilers, which were hard to merge. And this caused a problem in the development of the whole stack. And we basically want to prevent this with the gym. So we want to avoid that you have multiple non-compatible compilers. And instead, what the QGym aims to do is it aims to be to abstract away all the irrelevant parts so that it's really accessible for many different types of researchers or developers. And that's what you get out of the gym, namely eventually a trained agent that you can apply it to the device of your desire. So you can incorporate it in a compiler which you would like to work with. And the development, how we have done it is, it consists of general building blocks, so it's easy to add extra components, and consists of some visualizations and tools that make it easier to work with it. Well, then what does the QGym consist of? You can describe it quite compact. It consists of environments, namely the initial mapping, the scheduling, and the routing. And we have some templates. All the environments are built from a certain template. And if people want to play with it, they can build their own environments, or they can tweak existing environments in their own fork of the gym. And currently we're working on benchmarks. So what this will include, or what we try to help people with, is once they have trained an agent, they want to see how does it perform and how does it compare to existing compilers that do these specific tasks. We want to help them with that. Moreover, training also really depends a lot on what training data you put in, and somehow we also want to make it easier to make choices for the set of training data, because you can train a reinforcement learning agent on randomized data sets, but also on specific data sets or semi-random. And this impacts the performance of your agent? Well, we have a couple of design principles. First of all, it should be easy to use, and that's the case currently. You can just install the package and initialize an environment with a couple of lines. It's really customizable. You can customize your environments to your desire. And an important role in reinforcement learning is what kind of rewards you choose, and you can make your own reward functions or adjust existing reward functions. And yeah, as I said, you can also add your own environments. And it's platform independent. So yeah, we think it's quite accessible. And now I would like to go to an example. So how does the environment, how does QGIM work in practice? As an example, we will look at the process of routing. And what routing is about is, okay, you have the quantum circuit. And if you look at the quantum circuit, yes. If you look at the quantum circuit, you will see that there are 3 gates that are applied between 2 qubits. Namely, you have a gate, first of all, between qubit 2 and 1, then between qubit 1 and 0, then between 2 and 0. And for this very small example, we consider a hardware topology where you have 3 qubits with a length between 0 and 1 and 1 and 2. And if you want to execute this circuit on the topology, you will not be able to do it straight away because there is no link between qubit 0 and qubit 2. So what you need to do is to place a swap somewhere. And you can do it in this case by placing a swap between qubit 0 and qubit 1. And it will change the basically which logical qubit in your quantum circuit you relate to the physical qubit in your topology. And we have built an environment so that reinforcement learning agent can learn to place swap gates, and ideally to place as minimal swap gates as possible. So here in this animation, you see basically an agent at work. The white part is the part that the agent can see. We say, let the agent have an observation space of a certain number of gates ahead. It's not important per se for the agent what the gate is. It should apply, but it's only important between which qubits the gate should apply. So you see lines between qubits and not what gate it is about. And if you look now, there is a red line. This means that with the current mapping, this gate could not be executed. And then if the reinforcement learning agent tries to pass this gate, meaning that, okay, it could be executed, it will be penalized because it cannot be executed. So then it is forced to place a swap gate until it can pass the gate. And every moment in time, it has the choice to either place a swap gate between some of the qubits or to go further. And if it wants to go further, but it cannot go further, it will be penalized. And it will also be penalized for placing many swaps. And basically, this very simple way of looking at the problem, the agent should, in an iterative way, for for many different circuits. It should learn how to map it optimally, or to route it optimally for this given topology.
All right, yeah, Willem, thanks so much. We do have a bit of a tight schedule here, so we're gonna just need to keep the show rolling here. But really appreciate your talk. Again, for everybody in the chat, Willem will be on the Discord as well. So if you have any questions for Willem, please head over there, and that's where we'll continue the talk. Just maybe one quick question, actually, Willem. I'm curious. Do you have a background in computer science or in quantum or physics?
I have a background in mathematics and physics, but yeah.
Okay, well, nice, cool. Well, Willem, thanks so much for joining us here at QHack. Really appreciate your talk. And I am Dutch. Let me just see if I can get this right. Dank u wel and tot ziens.
Yeah, zeker.
Awesome. All right, thanks. Goodbye. All right, everybody. That was our first talk. We do have a jam-packed schedule up ahead here. So next up is Kohei from U of T. So stick around for that. We will be back very, very shortly. Yeah, hold tight. All right, everybody, welcome back. We have another talk lined up for you right now from Kohei from the University of Toronto. After this talk, we will be having like about a 30-minute break. Go grab some coffee, get a snack, whatever you need to do. But we'll be back at 11 after this talk, or back at 11:30 after this talk. Right, so let's get to our next speaker, which is Kohei. Kohei is is a postdoc at the University of Toronto's Matter Lab under Alan Asper-Gutziek. He specializes in quantum computing and its applications. He's joining us literally a stone's throw from the Xanadu headquarters here in Toronto. Kohei, it's awesome to have you at QHack. How are you doing today?
Very good. Thank you.
Awesome. Well, okay, let's hear about your talk. The floor is all yours.
Okay. Yeah, thank you for having me. Hi, everyone. I'm Kohei Nakaji from the University of Toronto. Today, I will talk with the title, The Generative Quantum Eigensolver and its Application for Ground State Search. This is the collaborative work with the NVIDIA quantum team. So, quantum computer has been developed rapidly. This is a beautiful image of quantum computer generated by generative AI. Well, so generative AI is also improving. Actually, this slide represents what I want to talk about today. So quantum computer has been developed rapidly, and generative AI is also improving rapidly. Then why don't we combine those two? Generative AI for quantum. This is the main topic of today's talk. As a conventional near-term quantum algorithms, in this decade, variational quantum algorithm, VQA, has been actively studied. The input of variational quantum algorithm is the structure of the parameterized quantum circuit and the definition of the cost function. And as a result of the optimization, we get optimal feeder parameters as an output, and we get the minimum value of the cost function in the ideal case. And there are many variants of VQA, like for ground state search, for machine learning, for time evolution, and so on. And it is, it has been actively studied in this decade. However, there are scalability issues in VQA. What we expect in the optimization of VQA is that optimization directly goes to the global minima. But in reality, there are scalability issues like barren plateau problem or many local minima, many measurements. And those scalability issues become severer when we increase the problem size or number of qubits. So we definitely need a near-term algorithm beyond VQA. So as a new concept beyond VQA, we recently come up with a concept called generative quantum eigensolver, utilizing the generative model of quantum circuits. In GQE, the neural network generates quantum circuits, and we calculate the corresponding cost function, and we calculate the feedback to the neural network. And by repeating this process, we train the neural network so that it generates quantum circuits having lower cost value. As a proof of concept, we created an algorithm called GPT-QE for ground state search. So the cost function is energy, ground state search, and utilizing the pre-trainable transformer implementation. So in the rest of the talk, I will talk about GPT-QE in detail. Specifically, I will talk about how neural networks generate quantum circuits and how we calculate the feedback to the neural network. And also, because GPT-QE also has a function of pre-training, so I will also talk about how we pre-train the neural network. So first, let me talk about how neural networks generate quantum circuits. So as I said before, in our GPT-QE, we utilize transformer. And transformer generate a sequence of tokens. In case of the large language model like ChatGPT, each token is mapped to a word by using predefined vocabulary. So the sequence of tokens is mapped to a sequence of words meaning sentence. In case of GPT-QE, each token is mapped to a certain circuit component by using predefined operator pool. So the sequence of tokens is mapped to the sequence of circuit components, meaning a quantum circuit. By using this quantum circuit, we can calculate the corresponding energy by using quantum device as an expectation value of an observable Hamiltonian. So this is how the transformer generates quantum circuit. And this is an example of a quantum circuit generated by transformer. So these 58, 53 are a sequence of tokens. And those tokens are mapped to circuit components. And in this example, we utilize, as an operator pool, we utilize exponential IPJ-TJ. So, well, this is the first, as far as we know, this is the first quantum circuit generated by transformer. So this is a process to generate quantum circuits by using transformer. Then how we calculate the feedback to the neural network transformer. To see how we calculate the feedback to the transformer, we need to see how transformer generate each token in detail. The process of generating sequence of tokens is like step-by-step process. In the first step, without any input, transformer generates logit, which is a vector. And according to the logit, the first token, J1, is sampled with this probability. And in the second step, J1 is used as an input, and the logic is calculated as an output. And according to the logic, the second token is sampled. And by repeating this process, we can get the sequence of tokens. And as I said before, the sequence of tokens is mapped to the sequence of circuit components, a quantum circuit, and we can calculate the corresponding energy by using quantum device. To build the procedure to calculate the feedback to the transformer, we utilize the following insights. So the probability that the sequence J vector is sampled is proportional to exponential minus beta W sum J vector. We can easily check that because the probability that each token is generated is exponential minus beta Wj1, exponential minus Wj2. So the probability that each sequence of token is generated is the product of those probabilities. So that's why it's exponential minus beta W sum J. Then if this W sum J vector is exactly equals to energy value EJ calculated by the quantum device, then the ground state is likely to be generated. From these insights, we create a technique called logic matching, which matches the value of W sum calculated by transformer with energy value calculated by quantum device. So this is a whole process of training, the whole training process in GPT-QE. Transformer generate sequence of tokens and also calculate the logit sum. And we, by using quantum device, we calculate the corresponding energy. And we calculate the cost by using logic matching technique. And by using backpropagation, we can update the parameters inside transformer. By repeating this process, we train transformer so that low energy state is likely to be generated. These are the results of the ground state search using the electronic structure Hamiltonians by using GPT-QE. As an operator pool, we choose unitary coupled cluster operators. And as a quantum device, we utilize actually simulator implemented by CUDA quantum provided by NVIDIA quantum team. So the horizontal axis is bond length, and the vertical axis is the energy value. And these dotted lines is the result of Hartree-Fock calculation, and this black line is a result of exact calculation, and this green dots are the results of GPT-QE. So by this results, we see that the training of GPT-QE properly works at least. So this is how the training process in GPT-QE works. So finally, let me briefly talk about how we pre-train transformer. So in the process of training, we don't need any data sets. But we can see that in this training process, we can aggregate the data given by a pair of quantum circuit and corresponding energy, because we run the quantum device repeatedly. So we can aggregate the data set given by a pair of quantum circuit and corresponding energy. This created data set is actually usable to train the transformer without running a quantum computer. So this data set can be inputted as used as an input of transformer, and we calculate logit sums, and we calculate the cost by using the data set, and we can update the parameters of transformer by using backpropagation without quantum device. We call this process as pre-training. So we can pre-train the transformer with the data set and then train the transformer with quantum device. And actually, I don't talk about it in detail because of the limitation of the time, but we actually verified that procedure using pre-training and training improves the quality of the ground state search. And we also identified promising scenario utilizing for pre-training. So, as I talked, in GPT-QE, neural network generate quantum circuits, and we calculate the feedback using logic matching cost. And we can also pre-train the neural network by using generated data set. So this is how GQE, generative quantum eigensolver, work. So this is a summary of today's talk. The variational quantum algorithm, VQA, has obtained considerable interest as a near-term algorithm in this decade, but is currently hampered by scalability issues. We believe that the solution to the issue lies in AI. We have introduced GQE as a new concept for near-term algorithm and have demonstrated its viability through the GPT-QE for ground state search. As a future work, conducting experiments with large molecules and utilizing actual quantum devices will be, possible future work. And enhancing algorithm and exploring diverse applications like in VQA is also promising, future work. And also, we will make the code open source as early as possible. So, I want you guys to join this hot field. Thank you for listening.
All right, Kohei, thanks so much. Oh, you got a thank you slide up there. I'll leave that up. Cool, awesome. That's a big group. Nice.
Yes.
Yeah, there was quite a bit of questions in the chat. Actually, I think one of our mods put in the paper, the archive link for your GPT-QE paper. So go check that out as well if you want to have another have a more detailed look at Kohei's presentation. We do have some questions from the chat though. You might need to flick through some of your slides too here, Kohei. So, but we have a question from Dentucky Kirby asking, the sequence of tokens looks an awful lot like an RBM. Is there anything there, or is that just a coincidence? So for those of you who don't know, an RBM is a restricted Boltzmann machine. It's a bit of like, it's an old generative model kind of thing. Yeah, I think this slide right here.
Okay.
The J1 and J2s, yeah.
So the question would be like, it resembles the restricted Boltzmann machine.
Well, I guess like the weights here, e to the minus beta w, like that's
okay.
Yeah, that looks like a it's a Boltzmann distribution. I know we're in the context of machine learning, so restricted Boltzmann machine. Yeah, I don't know. Is that just a coincidence or anything there?
Well, it's not a coincidence actually. Restricted Boltzmann machine is actually inspired by the physical intuitions, right?
Right.
And also the sampling process in transformer is also inspired by the physical inspiration. So that's why I think it's not a coincidence. Actually, this exponential by the minus beta w thing is not what we invented, which is actually the conventional way to utilize transformer as a sampler. So, yeah.
Cool. Okay.
Does it answer the question?
Yeah, I think so. That's good. And again, any further questions for Kohei, feel free to answer them or ask them in the chat still, or you'll be on Discord later too. Okay, we have another question from Latris17. They say, I have a question. Is the transfer also minimizing the circuit, like the number of gates used?
That's a very good question. So far we don't minimize the number of tokens. I mean, number of the depth of the circuit so far, but I think it's possible.
Interesting. Okay.
So it's it's a good it's also a good direction for the future research, definitely.
Right. Okay. Another question from Quantum Palace. By exact calculation, I think maybe at some point in your presentation you'd said like there's an exact calculation happening.
Yeah.
By exact calculation, do you mean exact diagonalization? There are no analytical solutions for these kinds of Hamiltonians as far as I know.
Yes, exact diagonalization. That's true. Because this is a simulation and the size is not so large, so we can calculate that we can perform the exact diagonalization.
Okay, cool.
So that's why.
Nice. All right. Another question from Andresulid. What type of optimizer is used? One that computes derivatives directly or one that does not rely on derivatives?
So it relies on derivative definitely because we utilize the backpropagation.
Right.
And so it relies on the derivative, and we utilize the Adam as an optimizer.
Right. Okay. One more question from Quantum Palace. Which part is quantum and which part is classical? So I believe the generating algorithm is 100% classical and the energy landscape is quantum. That's what they say.
Yes. Yeah, that's true.
Okay.
Perfect. So the only place quantum is involved is this energy calculation part.
Awesome. Okay. Those are some good questions. Again, everybody, people will be on, Kohei will be on the Discord after the talk here. So go on the Discord and ask Kohei some more questions. I see some people maybe trying to follow up with some questions. Great chance to go over to the Discord and join Kohei there. Kohei, we'll say goodbye here for now, but thank you so much for joining us at QHack. It was lovely to have you. Hope you enjoy the day today in Toronto. It's a little muggy out, but maybe go get some fresh air after your talk. Thanks so much for joining us. Take care.
My pleasure. Thank you so much.
All right. Cheers. Okay, everybody. We still have more to come today. We're going to take a quick break for about half an hour. After Kohei's talk, we have a talk from Agnostiq. It won't be Santosh joining us. There was a bit of a snafu there, so Santosh will be joining us. It'll be somebody else from Agnostiq. I actually learned that it's agnostic the other day, not Agnostiq. My bad. Right, come back at 11:30 for that. Let's also check out the QHack.ai website because there's some stuff going on there. First off, let's just go to the challenge portal here. So the coding challenges opened on Monday this week, and we have already a handful of teams that have solved all of the problems. So congratulations. Every single year, it's just like kind of blows my mind that people are able to solve all these. Seriously, because like we try to make them harder every single year. We try and intentionally make it so that people don't solve all of them. But hey, sometimes it still happens. We have some smart cookies out there. There's still time to submit stuff to the platform and like get points and all that stuff. So even though there's people that have completed it already, the competition's not over. Definitely continue trying to complete all the questions. I think they close tomorrow morning, or I can't remember the exact time, but they close sometime tomorrow. And the open hackathon will open tomorrow as well, which there is information right here on the QHack website as well. Oh, it rerouted me weird. There we go. There we go. Hackathon challenges. Oh, I was here already. Anyway, I was here on the dashboard already. Okay, so once the open hackathon opens, you'll be able to access this tab here. There's categories of things. Definitely go check it all out. That will open sometime tomorrow. All right, thanks again to our sponsors. Really appreciate all that you do. Everybody here has helped out quite a bit with making QHack possible, so thanks so much to all of our sponsors. We really do appreciate everything that you've done for us. We're going to be back at 11:30 Eastern time. So don't go anywhere. Grab some coffee. Maybe, well, you have to go somewhere to get the coffee. I'm rambling at this point. We'll see you at 11:30 for a talk with Agnostiq. Agnostiq. Cheers. All right, everybody, we are back for another couple of talks here before we go on a bit of a lunch break. We're joined by Agnostiq, not Agnostiq, as I've come to figure out, Agnostiq right now. It is Ara from Agnostiq. How's it going, Ara?
Going great.
Awesome stuff. Okay, so you're here to talk to us about quantum data structures from classical noise. We'll get to your presentation in just a second. So everybody, put your questions in the chat if you do have any questions for Ara. Ara will also be in the Discord after the talk as well. So if you have questions that didn't get answered here, go to the Discord, and that's where it will be happening afterwards. All right, the floor is yours, Ara, so take it away.
Okay. Hi, everyone. Thanks so much for being here. You've seen the program. I'm actually not Santosh, unfortunately. He's come down with the flu, so I'm substituting for him today. I'll do my best to give the presentation, but please bear with me if I misstate anything. Hopefully we can have some interesting discussions about it. So like Isaac said, I'll be talking to you about learning quantum data structures from classical noise. And without further ado, let's get into it. Okay, so brief outline. First, we'll discuss the goal of what we're doing. I'll present the not too complicated algorithm that accomplishes that goal. We'll look at some early results and then discuss a simple use case for this, okay? So what we want to do is to take discrete samples from what might be called a hard data distribution and use them to learn the underlying fundamental distribution. So a hard distribution might be something that's sparse or multidimensional or otherwise just difficult to capture in a small number of samples. What we're going to do is have a quantum circuit that we use as a learner that's actually able to do this capturing more efficiently than would be without it, right? Okay, so basics of the algorithm. We're going to have two steps here. They're going to be training and generation. And in the training step, we're going to take a handful of points from the hard distribution, and we are going to embed them in the Hilbert space. And then we're going to learn the process that evolves these embedded points into an easy points from an easy distribution. So what's easy may be like Gaussian noise or something like that. So very simple to understand, very simple to capture and quantify. That will be the training step. And then the generation step will essentially do this backwards. So we'll embed easy states and use the circuit with the optimal parameters to transform them into points that are representative of the difficult distribution. If this sounds familiar to you at all, this is sort of pretty typical of a diffusion network kind of setup in classical machine learning. And at the bottom here, I have sort of a visual representation of what that might look like. Now, my hard data here, you can see my mouse, yes. So the hard data here is just an S-curve data set. It's not actually difficult, but just for the purposes of the demonstration, that's what we'll use. And my easy data is just Gaussian noise. And what will happen is the training step will run from right to left here. So we'll sample points from the hard distribution, and we'll slowly transform them into noise. And then the generation step will go left to right, taking the noise back into the hard distribution. So if we want to look at this a little bit more technically, we can think of having a state that's representative of the noise data embedded in Hilbert space, and we are learning a transformation that can take that state into a state that's representative of the difficult data also in Hilbert space. And breaking that down, so we can actually do this with arbitrary complexity. So we can think about having however many time evolution steps that little by little transition one data point into the other. Or we can actually just fold this trivially and just try to do it in a single step. It's rather open-ended, exactly how you want to implement this. So here's an example of like the minimal version. And I have on the right just some penny lane code that will implement the learner circuit in this case. Now, I hope this looks familiar to everyone. There's nothing too crazy happening here at all. I have a simple projector matrix, and I'm defining a Q node over here with some device. And then the actual embedding that happens, I'm just going to use the QAOA embedding template to do this. Now, you'll note there's actually no explicit time evolution happening here. And like I said, this is the minimal version of the algorithm. We're just going to pretend that there's one step, and we can take the noise data to the difficult, important data just by learning a single evolution step. So one thing about this circuit is that you can see it actually grows exponentially in size. Not the circuit, sorry. The projector that the circuit uses grows exponentially. So this is okay if we have, say, 2 to 10 wires, but it's going to take up a lot of memory if this projector becomes, billions of units wide. So you can actually do a swap test circuit to do the same thing if you want to do it more memory efficiently, but this is going to work for us. Here's a slightly more pictorial representation of the same idea. There are 3 learnable parameters in this case. So that's going to be parameters for the data space embedding, parameters for the noise space embedding, as well as the Hamiltonian process. Now, the third thing I have neglected for the purposes of this example. But as far as the first 2, if I just go back to my circuit here, you can see that over here, I have 2 sets of parameters, namely alpha 1 and alpha 2, and then I have my data and my noise here. This looks a lot like a kernel circuit, if anyone here is familiar with that, but strictly speaking, it is not a kernel circuit because these parameters are, in general, different, alpha 1 and alpha 2. And what we're looking at conceptually is that we have a Hilbert space that's determined by our circuit. And we're going to embed the 2 points there, and we're going to work entirely in Hilbert space to try to turn one into the other. And in the end, we have something that can take just very easy to sample data, even a single data point, and via the transformation recover a distribution that's representative of the more complex data. And what points in that distribution will look like is there'll be a weighted superposition of the data points that we sampled with the weights determined by the noise points that we put in. Okay. Now, let's look at some early results. And before I do that, just a quick plug for Covalent. So Covalent is a workflow orchestration platform. It lets you design complex workflows, run them in the cloud. If you don't have the compute on your laptop, it's super easy to use and Pythonic. Covalent Cloud is the paid version of that adds enterprise features and sharing and better hardware availability as well. I'll have a link at the end if anyone's curious to check that out. And what I have on this next slide is the Covalent workflow that generated the results that I'm going to show you shortly. So what you're seeing right now is a directed acyclic graph, which is just a fancy way of saying a kind of like a process made of a bunch of different nodes that goes from top to bottom in this case. And what's happening here is I'm running a workflow that does the training and generation process for 3 different data sets. And one of these will be the S-curve that we saw earlier. And then I believe I have a circles data set and a moons data set. These are sort of just standard data sets from scikit-learn. Maybe lots of them will be familiar to you. And yeah, so that's reflected in the shape of the transport graph that we're seeing here. You can see distinctly we have 3 different branches over here. What's cool about this is that the code for this is just a for loop over the 3 data sets, and Covalent figures out that, yeah, I can actually do this in parallel. I can run the 3 branches independently, combine the results at the end, and send them back to the user. But anyways, moving on. Oh, where's my, okay. I would like my GIFs to play correctly, but unfortunately, okay, now they've all stopped. Okay, let me see if I can get this going because it's pretty cool. Well, back in, there we go. So hopefully you can see it happens rather quickly, as you can tell from the loss curve here. So most of the change happens maybe in the first fifth of the length of the GIF. But what happens is we go from a background of just complete noise. Overlaid on top of it is the original data distribution, which is to represent the hard data in this case. And what you can see is the noise in the background sort of changing density over time to match the distribution in either case. I'll play that one more time just for fun. See it come out. And indeed, what this is, what the animation is just steps in the training process outputted as images that I've combined into a GIF. And we see, indeed, in each case, it trains, the model trains. This is a very typical loss curve you see from a successful training run. What we're seeing on the bottom is a metric called the Wasserstein distance. I hope I'm pronouncing that correctly. What that is it's also known as the Earth mover distance. So that's going to be the amount of effort quantified numerically to turn one distribution into another. And the way I'm comparing these two things is I'm taking a kernel density estimation based on the real data points, and then that gives me a distribution that I can compare to the target distribution. So how do we verify that this is actually learning? Well, apart from our wonderful loss curves, we want to test that the model actually performs the way that we expect it and that it fulfills our goal. So if you remember, our goal was initially to capture a difficult to represent and difficult to sample distribution by training our circuit such that we can take points that are easy to sample, put them through our circuit, and recover the difficult distribution. And that's what we're seeing here. So here we have two figures side by side. Overlaid on top of the grayscale stuff in the back are these red data points. So these are just data points from Gaussian noise. Now, Gaussian noise is the easy data, right? So on the left, I have Gaussian noise, which I didn't use to train my model. In this case, I'm sampling some of these points over here, which are not too far from the center where the real data is. But because these points are not the ones that I trained with, you can see that the distribution that I get back is actually not the S-curve. Maybe arguably it's a little bit similar, but it's certainly not the beautiful, it's not that pretty, but the S-curve that I see on the right. So here on the right, when I sample points from a distribution that I actually used to train the model, these little red dots, even just one, I can recover the point density from the quote unquote difficult distribution, which is the S-curve in this example. Okay, and a little bit more math. This is just our training process. And to reiterate, what I get back when I put in a noise point is a weighted superposition of the difficult points that I sampled, which gives me, lets me recover some representation of that difficult distribution simply by just putting in one point of noise. The one catch here is that the output data is only accessible as a quantum state. And tied to that are all the difficulties that come with it. Okay, that's all for me. On this last slide, I have a QR code that'll take you to the main Covalent website. We have our open source repo at agnostichq/covalent. Check it out. It's free to use. And if you do check it out, please give us a star. We would really appreciate that. We're also on socials on X, formerly known as Twitter. And yeah, you can see all that here. So I'll leave this slide up for a little bit. And that's it for me. Thanks so much.
All right. Thanks a lot, Ara. Really appreciate that. You did a really good job. Like you said at the start, bear with me here, just kind of pick this up. How long did you have to prep for this talk?
About an hour and a half while I was already doing something else. So
nice. I think that's pretty impressive. So maybe we can get some claps in the chat for Ara. That was really good. So you'll be in Discord. Will you be in Discord specifically, or will somebody else from Agnostiq be in the Discord?
So my colleague Ian is in there right now.
Yep.
I will also join in a little bit.
Cool. Yeah, Ian is in the chat as well. Hi, Ian. Thanks for joining.
Santosh might be in there as well.
Okay.
Sure,
Cool. All right. So we have a question from Dentucky Kirby. This is really interesting, but what is the purpose of learning quantum stuff from noise that is classical? It has no quantum stuff in it, so are we manifesting quantum stuff from nothing?
I wouldn't necessarily put it that way. So I think a better way to think about the goal here is that you have real data at both ends. So you have two pieces of real data, or rather real data distributions. One is easy for you to access because you can just, it's Gaussian noise. The other is something difficult. And what we're doing is using the quantum stuff in the middle just as a way to get from the easy stuff to the hard stuff. So the hard distribution will be difficult to understand and fully capture with a few number of samples. But hopefully, when we train our quantum circuit, you can put in easy data and take a shortcut through it to the difficult data without having to manually sample the difficult data. So the goals are entirely real. The quantum bits in the middle are just to facilitate the goal. I hope that.
Yeah, that's clear. Is there any, I guess, is there any application, or I guess, is there anything useful to extract from like the intermediate representation of the data in the classical realm, or are we like maybe that was the part of the question there that Dentucky Kirby meant?
It's difficult to think conceptually about quantum data, at least for me. But the one kernel of understandable bit here, I think, is that the quantum data will be some superposition of the actual points, the small number of points that you're able to get from the difficult data. So based on how we manipulate that superposition, we can turn it into sort of a blurry, kind of hopefully accurate version of the actual data. That's kind of the main quantum-ish thing that we're using here, is a weighted superposition of the real points, weighted in a very learned and trained way.
Right. Okay, cool. Another question from Ivana. I have to admit, I haven't used covalent very often yet. How difficult is it actually to get started properly?
Not at all. It's totally in Python, and I suppose the one prerequisite is that you have your code arranged into a bunch of neat functions, totally normal functions. But yeah, that's about it. And then you take that, put a bunch of decorators on top, and you're good to go. We have a quick start guide on our website, covalent.xyz, which I believe the QR code will take you to. Oh, sorry, the quick start is in our docs, which is one click from the website. I would say check that out because it'll get you started right away. It's totally simple, I promise.
Cool. I'm going to leave this slide up here a bit more for people in the chat in case you want to go check the website out and scan that QR code. Okay, one more question from Catalina. Do you use PennyLane often?
Yeah. Oh, it's actually my go-to. So I've spoken with some people at IBM, and I've told them how much I like PennyLane over Qiskit. Yeah.
Nice. Okay, cool. All right. Well, if there's any more questions for Ara, please head on over to the Discord. Ara and Ian will be there to answer your questions. That's really awesome of you guys both to do that. Really appreciate it. Yeah, I think that's it for now, Ara. So we'll say goodbye and see you in the Discord.
All right. Thanks, Isaac.
All right. Cheers. Okay, so next up, everybody, we have a talk from Akash from qBraid. We're going to just kind of talk about qBraid in general. Also, on the QHack website, on the coding challenges, it's possible for you to open up the coding challenges in qBraid as well. So you can like copy the coding challenge code and paste it in your favorite IDE, or qBraid's made it possible to like just open everything in qBraid. And if you don't know what qBraid is, well, stick around because Akash is going to tell you more about it. So we will be right back in about 10 minutes. Don't go anywhere, and we'll see you in a bit with Akash. All right. Hey, everybody. Sorry about that. We're here with Akash. He's going to talk about qBraid. Now, for those of you who don't know, qBraid is sponsored for this year's QHack, and you can actually open up all the coding challenges within qBraid itself. So Akash is a quantum cloud architect at qBraid, and he's joining us right now. Akash, how's it going?
Hello, Isaac. It's going good. How are you?
I'm peachy here. I'm doing well.
Yeah. It's
All
been
right.
a hectic morning for you.
What's that? Sorry.
It's been a hectic morning for you.
Not too hectic. No, everything's running pretty on time. So yeah. But anyway, here, let's get your talk going. You're here to talk about qBraid. So floor is yours.
Hello, everyone. I'm Akash. I'm with qBraid since about a year, and I'm a quantum cloud architect with qBraid. And together we are bridging the future and bridging the gap between quantum hardware, software, and users, with the nudge on the users a bit more, because that's the whole thing that will take the ecosystem forward. So I'll go ahead about with the introduction. It's going about, sorry.
Oh yeah, no worries.
Yeah, so today's talk would be like braiding the future and the gap between the quantum hardware, software, and users. So like we see, there are a few other things with the quantum thing, but I'll go into that during a talk. So hello everyone, like I'm Akash Kant, and I'm good morning to you, and great to know all of you together here, and all the hackers that have come here, and I welcome you to my talk. I'm happy to, as the hackers here, have chosen the quantum computing field rather than just going through AI, ML, blockchain, and etc., and given dedicated the week to quantum computing in this case. And I'm happy to actually represent qBraid in that aspect. There's a lot of more things that have been increasing in the space of the hackathon, and I can assure you I've been with you guys during the whole hackathon, and I actually like the vigor and the enthusiasm during the initial time when you were submitting the submissions and everything, and I was supporting you guys on the back end. But believe me, that's like a very interesting place to be at. So basically, this is a very generic view of the quantum computing and the classical computing and how the power is exponential. I will skip to the next slide. So basically, where we are is the noisy intermediate NISQ state, which is the intermediate scale quantum. So it was referenced by 2018 by Dr. Preskill. After that, we are trying to go around how do we make the fluctuations. So basically, I'm talking about how quantum would scale in the future and how it goes about it. So basically, after the NISQ, the secondary thing is size of devices, which I'm pretty sure most of the folks here are trying to use and do it. So basically, we had quantum hack. We did have quantum devices by Cura, Quantinium, IonQ, which were actually reaching the fidelity of not 9s, but at least 99 point something. So this is a very, very exciting place to be at. But I think it will grow in the further, and as people and as more students and researchers are going about it, this thing is bound to be solved, at least not at the right state of NISQ, at the perfect thing which we think and know, but ways around it with the other aspects of it, like how AI and ML would have helped to do error mitigation. So similarly, not exactly on the artificial intelligence side, just more on the how do we solve error correction for the quantum. So that's a very interesting place to be at. Similarly, how NISQ will go about is it's right now at HP NISQ and FTQC. So we'll talk about this, how the collaboration in quantum systems goes about. So what are we talking about is the decoherence, how the calibration errors are there, how do we measure the fidelity and the gate fidelity. So we are solving each one of them one by one, and as soon as we go forward, we'll be able to get more aspect, at least more data on which path to take. So there's a numerous path, and we have to decide on which paths to take and explore. And if not, retrace back, like put an idea, a thought, test the thought. If it doesn't work, like any science experiment, move on to the next part and on with it. So this is the thing which I talked about is NISQ. There's something called HPNIS, which is high performance. Luckily, qBraid is part of some of the projects which are requiring to do high performance compute in the future, and also FTQC, which is fault tolerant QC, which will be relatively not exactly fault tolerant per se, but reaching 9s fidelity, what we can call it as like it's better than 6 sigma, so we'll just go for it. So right now we are at the ENIAC moment, but ENIAC had the computers during the 1960s, 70s. But moving further, we'll go ahead and actually solve multiple things, and it's a journey, and we all will be a part of it. So that's the fun part of it. So now I'll walk you through the application development experience. The application development experience, how do we solve like I'm pretty sure most people during the hackathon have moved on one step ahead of it, with giving the gate circuits and the fidelity, and how do we go about it. So basically you call in QC expert. This is for the industry level. How do we want to test a POC if need be? Then calling an industry expert or the domain expert in this use case, then go about calling a hardware expert to get the hardware, and then go about setting up the quantum compute and resources which are bound to scale for different users, and how do we go use those in real life example and at scale. So all of these processes, we are at step 1, possibly step 2, solving step 3. Ideally, I would love that in the future you guys become the step 2 part and actually solve QC experts and domain as the use cases come up. We are quite hopeful, with the fingers crossed, being that the hardware experts choose the quantum computer and make millions of the contract is signed even and reduce the cost similarly for people to onboard and use, rather than having a gate blocker of such a high dollar value to each of them. But similarly, as things get solved, it will get, as things are growing. So that's where qBraid comes in. It's not exactly how how do we actually focus. So basically, there's so many nudges to actually start a quantum computer, trying different circuits. There are different things launching. There are different like a penny lane has a few 0.27 was before that. Right now it's 0.34. Similarly, there would be some other combinations which you like to use on the quantum ecosystem, but then you end up trying to solve, okay, fine, I'm getting some pip install error or some ecosystem error or some environment errors, or just connecting to a device, solving one of the state in a chasm circuit and converting to a different one would cause an issue and something will break. So at least those are the less important part as part of your projects or questioning. So we are trying a level best to actually solve it for you, which during the hackathon you might have seen. It could like, at least that's what I think. It was a very seamless entry with the challenges and everything, and that's where we come. So we want to take your painstaking parts, solve it, and just keep quantum on the table for you guys. So that's been what qBraid is trying to do. So it's a leading cloud platform with around 10K users still now, and I'm hopeful after this it will grow to further heights. We do provide CPUs, GPUs, QPUs, and software tools. During the hackathon, we did actually give jobs and devices with the penny lane circuit, And we were actually enabling that so that people can see the jobs and devices, even though none of the penny lane challenges are there, but this will be the interface for the jobs, devices, sending a job through, and it will be as simple as just copying a link and then sending it through. And the other configurations which we'll manage, which we'll talk about in the qBraid SDK. There are some, we also sponsor a few of the open source project as part of Python Toolkit, which is the SDK, and which I think you guys should actually try. And the other thing is we are tailored a lot of hackathon, and we have this configuration for penny lane for the daily users need. But there's a lot of other configurations on the qBraid side, which I think and which is very relatively easy to use and go about further. So what does qBraid offer? So basically, I'll talk about what is qBraid Learn. We launch quantum computing for a fraction of the cost, and it's kind of scaled through. It starts under 5 minutes. So basically, if you want to give a demo or something, and you know that's something that should work with the environments and the other aspects around an environment, and suddenly something doesn't fail, you can use the lab, and it's you could run on a Chromebook if you want, and the performance and everything should be the same. Similarly for the qBraid SDK, even if you want to like connect your SDK using qBraid platform or your local platform from your VS Code or some other Jupyter Hub, by setting up an SDK or API key, you can use it, and all the other systems will work flawlessly. And then we also part of some of the research projects, which I'll talk through. Of course, which is given the qBraid docs. The lab is what you guys use during the whole hackathon, and it was quite easily, even with the seamless entry of Xanadu QHack with qBraid, and it was just one click, and it opens the notebook to you on a server and does everything for you. This is classical stack, which we talked about, and which we're trying to overdo, and we want to give you the quantum stack. Meanwhile, we are also tackling the quantum stack problems so that you can actually and then make the wheel possibly an alloy wheel set or something like that. Let's going further. So we have the qBraid lab. It's a funny environment thing which we made. It's like, okay, it integrates with your environment, does your changes, gives you GitHub and all the major quantum SDKs onto it. Now we'll move on to the lab, which you guys have used. It has a connection with other parts, which is brackets, so you can use any of the environments. It will majorly close for this, but if you want to use it, or you can try qBraid, or we can talk and get those things out for you. So, and these are there. So there are a few other tutorials. So if you want to get started onto that, you can use the tutorials or code snippets. You can just click on the code snippets, and the code snippets will be launched to your Jupyter. Similarly, the SDK, which is also available on platform and online on your local machine, just by a set of configuration steps which are given on the open source GitHub repo. You can actually see that. It's the transpiler between all these different variations, and we actually have a weighted map to transpile and take the best transpilation across. We have Circ program, that we have PyQuil, Bracket, Penny Quantum. We also empower other ecosystems so that we can scale faster, like AWS, all these different aspects, turning to the qBraid SDK and connecting to all the other one. And there are a lot of issues because there are too few different systems all talking and configuring with the others, but sometimes some takes a release up and the other one does not. So there's a lot of headaches if you actually want to do a research and do benchmarking on different aspects of this. So then there is something which we can solve faster. And this, we are part of the SDK program, which has this Rigetti QHack. We have supported different hackathons, even QHack for this year. We have also made the SDK open source, and there's a lot of downloads around it, which I think you guys should try and see. We were part of the Unitary hack. Also, going further, we had a best on inflection of the quantum compatible softwares and hardwares, and you can see different hardwares and softwares, which is given. We're part of the research. We have given some papers. We are part of the Welcome League program for Q for Bio. So I think quantum would impact chemistry, biology, and all of these aspects first, because these are unsolved problems which are quantum possibly quantum in nature. So we can tackle those first, which has a wider impact. And these were the problems which are limited by the computational power. And right now we can solve those and use it in different aspect of optimization or controlling or just finding all the other applications around it. Something like even in the challenge there was a problem called a simple totalization would be something which also tackles on the chemistry side. So you should like check this aspect of it and like what's the innovative thing which you're trying to tackle and use, and hopefully will be successful at that. So the last thing which I would like to try is like what we are trying to do is users and developers alike. So when I think the quantum advantage is not, even though we think quantum advantage, oh, it's a term that we can use and we are getting an advantage around it, but the major thing is if it's the people who are doing the quantum computing and have a quantum experience. I have taken a lot of interviews and I've seen that people with software engineering are able to try to tackle the quantum thing, but what's a better case, the quantum advantage would be like as the field grows, the number of quantum physicists, chemists, computation people would actually grow and the field will grow longer, and those guys will be tackling software engineering problems, not the other way around. And that's where the quantum advantage will lie. Once we are able to tackle those, we'll be going about how the rate of growth of the field will surpass the number of users, and that's where we are trying to figure out and how do we scale and reach that. So they are some other aspects which if you're upskilling yourself, like I've talked to some freshmen sophomore which have gotten a lot of knowledge on quantum computing, which is like I'm like super impressed about it. But going further, how do we actually use those people who are quite enthusiastic on this field and have a lot of vigor around it, learn all these software engineering basics, because eventually when everything will get solved which needs to be solved, it will come at the most imminent problem, which is scale and distributions. And that's the best challenge to solve after that. And once we are able to solve it, then only we would have reached the quantum advantage per se. And I would not leave. So basically, if you're having the advantage, you need to think about scale and distribution. If you're not leaving the former advantage to someone else, we might not even leave the latter to the others. So we'll have to think on both aspects and keep us upskilling ourselves. Because while we are doing some translations on different, like I could talk about this part, we were doing some translation on the SDK from different aspects of to different aspects. We see that while there were some issues, there were some of the software engineers who have done the quantum ecosystem, and there was some loopholes around it. And how do we think? So hence, I'm quite confident we will need in the future the other way around with quantum engineers solving software problems. And I'm pretty sure we are up for the task of doing that. The next suggestions would be like just trying to learn Git. It's very, very imminent in problem. The notebooks, Docker, K8s, these are that will help us grow and be quite of independent of any other aspects and moving parts and have a better control over our system. And that's where I say thank you. I'm from qBraid and this is Akash. And if I'll be around if you have any questions, and please, this is the QR code for the account. If you would like to try it out, I would suggest you should at least give it a try and see what all the devices. And I could think about the other environments that are there. There are some jobs, there are some devices, and just see what devices are there. And what we have done is kept an infrastructure which is quite easily scalable for any moving device that comes onto it. Give it to the user and have a vice versa circular loop around it. And that makes things easier, at least a one shot thing where we build things ourselves. And then as we finish it out, we can more about go through and then reuse those code and not like we said, we are not trying to reinvent the wheel, but sometimes we could change the wheel and put it into a different aspect and make it give it a better rubber tires and just like set it to the moon. So that's where we at. And that's been my talk. Thank you.
All right, thanks so much, Akash. I'll leave this slide up on the screen for a little bit, actually, so people can scan that QR code if they want. Thanks so much. That was really informative. Lots of stuff to go through there. We'll jump right into some questions. We have a question from Catalina. Is there a limit on the number of files or environments I can have?
The number of the good thing about is like there are some tier of credits which you can use, and once you have those credits, like it's very sub minimal, and it's kind of free also right now for most of the environments. But you can also use those environments to create your own environments and have a base copy, and those environments are being guaranteed by us. But the environments which you are creating, you can actually test it out on the base and then reuse onto your aspects. So they're no per se, all the environments which you can see are there, but if you would like to reuse those, you'll have to reuse it per se on different aspects.
I see. Another question from Catalina. Can I use codes for free AWS? Can I use codes for free AWS credits directly on qBraid?
Yes, not right now. You'll have to set up your own AWS private key and the secret, and then use that. But what we are trying to do about is we can also provide it as a service later on, but it's not about in the docket right now. But this is what we also have thought, giving the users their own personal thing, which can be managed by an organization and moving further as part of different aspects onto it. But if you're trying to set up your own AWS and that's also as per our use case. We have seen most users don't want to go through making an AWS account, calling an IAM user, setting up the IAM roles and permissions and things. So rather than just let it use it, and we have actually kept the rates of the devices without the IAM almost on a similar basis and par. So I think that's actually a very commendable thing to not think about rather than just focus on this. But yeah, we do have that in the docket to actually fill it out for the users to actually use their own AWS ID and secret, and your credits will not be charged in that case.
Nice.
But it's not available right now.
Cool. All right. So I think that'll do it for now. Again, if there's any questions that didn't get answered, go see Akash on the Discord. He'll be there. Akash, it was great to have you. Thanks so much for joining us today, and we'll see you around. Cheers.
Yeah, thank you.
All right, everybody. So I mentioned in the chat we'll be doing a giveaway. It seems my camera is actually a little bit delayed, which is probably really weird for everybody watching this. But anyway, I'm not sure what happened there. Okay, so we're going to be doing a giveaway right now. So for those of you who are active in the chat, you will be entered in a giveaway. Let me see here. Last chance. Anybody say something in the chat, and you will be entered in a giveaway to win some swag. And I'm rolling it. And nice. Okay, so Fyro's Black 12 has won the giveaway. Congratulations. Our moderators will get in touch with you. Basically, just whisper them on, or our moderators will whisper you on Twitch. So if you have do not take any whispers from strangers turned on in your settings, make sure to turn that off so that we can message you. They'll get your information, and we'll ship you some swag. So congratulations there. One more important thing to announce here. Right. So we have a power up. We're giving out some power ups for the Open Hackathon. So there's stuff that you can get to boost your Open Hackathon project, like hardware access and a bunch of whole other stuff. So there's a form on the QHack website that you need to go and fill out. Make sure you go and do that. But let's go to the next bit of the schedule here. So for today, we're going to be back at 1 o'clock, so about half an hour. We're going to hear from NVIDIA. That'll be fun. We have a few more talks lined up this afternoon. So get some lunch, maybe another coffee. I'm probably going to do that, another coffee and some lunch. And we'll see you back here at 1. We'll be hanging out in the chat, so if you do have any questions, fire away in the chat, or you can head on over to our Discord. Once again, thank you to all of our lovely sponsors who are giving talks. It wouldn't be possible without you, so we really do appreciate all that you've done for us in QHack this year. All right, everybody, we'll see you back here at about 1 o'clock with a talk from NVIDIA. So cheers. All right, everybody, welcome back. Hopefully, you got some lunch, or you're having lunch right now as you're watching this, or breakfast, or dinner, or wherever you're at. Thanks again for joining us. We have Jin-Sung Kim joining us from NVIDIA next. Jin-Sung Kim leads the partnerships and alliances for quantum computing at NVIDIA. He has a PhD from Princeton University, and prior to NVIDIA, he was a research staff member at IBM Quantum. Let's give a big warm welcome and applause to Jin-Sung for joining us today. How's it going, Jin-Sung?
It's doing well. How about you, Isaac?
Oh, I'm great. I think we were just chatting about the weather before we went live here, and in Toronto it started to just absolutely be a miserable blizzardy mess, and you're joining us from nice sunny San Francisco. It just looks absolutely gorgeous.
I don't know if you can see behind me. It's a beautiful day right now.
Awesome. All right. Well, hey, your talk is about quantum accelerated supercomputing and the NVIDIA quantum platform. The floor is yours to get going on that. Excited to hear it.
All right, thanks. Thanks for the introduction, Isaac, and thanks for having me here participating at QHack. So my name is Jin-Sung Kim. I'm from the quantum computing team at NVIDIA. Been at NVIDIA for about 2 years now, so I manage our partnerships and our alliances and all of our technical collaborations. Like Isaac mentioned, I used to be a research scientist at IBM Quantum for several years. Some of you may actually know me from my time there when I hosted Coding with Qiskit for a season. I did my PhD prior to that at Princeton, studying electron spins in silicon systems for their use as potential qubits. So I've been in the quantum computing game for a long time. So I'll be talking to you today about our platform, what kinds of things that we're doing to support quantum computing at NVIDIA, and how we see quantum fitting in with kind of the broader HPC and accelerated computing ecosystem. So just to take a little bit of a step back and talk a little bit about NVIDIA's history and who we are as a company. We, of course, invented and built the GPU systems that enable essentially all of modern AI, including ChatGPT. In addition to this, NVIDIA has a really long and storied history in supporting scientific computing, starting from the advent of CUDA. And if you're not familiar with what CUDA is the framework that we developed that enabled developers to start using GPUs as general purpose compute machines. And it's really the technology that brings things to life like ChatGPT. So what CUDA enabled developers to do, back in 2006 up to 2012, start to use GPUs as accelerated computing machines. So this really enabled the advent of things like deep learning, generative AI. The photo here is actually a picture of Jensen Huang, our CEO, hand-delivering the first DGX A100 systems to OpenAI. I believe Sam Altman is somewhere in that picture as well. And what we see in quantum computing is a lot of parallels to what generative AI and machine learning were, 10, 15 years ago. So NVIDIA has a long history of supporting scientific endeavors like this and trying to support developers and giving them the best tools possible to do accelerated computing and scientific computing in the most performant way possible. So what are we doing at NVIDIA? The number one question that we get for the quantum computing team is, are we building a quantum processor? And the answer is no. But we are building essentially all of the tooling and infrastructure around building a useful quantum computer of the future. So essentially all of quantum computing of the future, useful quantum computing will be some sort of hybrid workload. So quantum computers are very, very specialized, and we believe will be very good at solving certain classes of problems in the future. But alongside each one of these problems are very difficult HPC problems that will require a lot of accelerated computing and really requires a heterogeneous and hybrid method of actually programming useful quantum workflows. So what does this mean in practice? So what we've done is built a platform to enable what we call quantum accelerated supercomputing. So at the heart of this is our platform called CUDA Quantum. So this is our platform and programming model for programming hybrid quantum classical workloads. It enables you to build really fast, very performant and flexible workloads leveraging CPUs, GPUs, quantum processors, and physical quantum processors together. We also have a collection of libraries for doing accelerated simulation. So this is called QQuantum. This kind of sits on the back end and helps you accelerate quantum circuit simulations on GPU systems. We're seeing speedups of a couple of orders of magnitude faster. So if your simulations are taking a couple of hours, they'll run in a couple of seconds on a GPU system. So really, really fast performance. This really enables the community to run very fast algorithms and do fast iterations for application development. And finally, we have on the system side a method of tightly coupling GPU systems to actual quantum processors. So what we've done here is partnered with Quantum Machines, who provides quantum control hardware for various modalities of qubits. And we built a system called DGX Quantum. And this provides a very, very low latency link between a GPU system and the quantum control system for various qubit modalities. So what this enables is for folks to start to actually look at what real-time compute alongside a quantum processor looks like. So why is this important? For a lot of things like optimal control, calibration, error correction decoding, a lot of these things require pretty heavy-duty compute alongside an actual quantum processor. So having now a low latency link between these two things actually starts to enable users and developers to develop the error correction decoding schemes and things like optimal control schemes alongside the actual quantum hardware in real time. So a big part of our platform is to partner broadly across the entire quantum ecosystem. So we have a huge ecosystem of partners. We like to work with essentially everyone within the quantum computing ecosystem. So essentially every variety of quantum hardware builder, every qubit modality. We've accelerated essentially every quantum simulation framework. And we partner across a lot of application and algorithms developers as well, along with a lot of different quantum startups, as well as national labs and industry partners. So let me just take a beat here and talk about some of the success stories from our platform. So the first thing I want to highlight is our GPT quantum eigensolver work. This was done in collaboration with the University of Toronto and St. Jude Children's Research Hospital. This was work done with CUDA Quantum. So I think earlier in the day, the first author of this work, Kohei Nakaji, gave a really, really nice talk about this work. But essentially, what we did was develop a novel generative pre-trained transformer, or GPT method, for computing the ground state energy of molecules of interest. So this is a really, really awesome workload that lies at the intersection of generative AI and uses it towards quantum computing. So there's a lot of workloads that invoke quantum machine learning. This is kind of the inverse of that, where we use machine learning methods to actually enhance the output of a potential quantum processor. So this is the first demonstration of a GPT-generated quantum circuit in the literature, and it's a really powerful example of leveraging AI to accelerate quantum computing today. So kind of the way that you can think of it is we have a pool of operators that analogously can be treated as words in a large language model. And we train this model to actually generate sequences of these operators from this operator pool to give us quantum circuits that have desirable properties. So this is a pretty generalizable method. We can train it to do to give us circuits with various desirable properties. In this first instance, we focus on the problem of quantum chemistry. So we're finding very good ansatses for quantum chemistry problems. This was executed using CUDA Quantum. As I mentioned before, CUDA Quantum enables you to do hybrid quantum classical workloads very performantly, very flexibly. The platform was designed for workloads exactly like this to combine Gen AI and quantum computing in one workload. We ran this on a very powerful GPU system called Perlmutter, which is a supercomputer hosted at Lawrence Berkeley National Labs in their NERSC facility. And we think this really opens the door to a wide variety of novel generative quantum algorithms for things like drug discovery, material science, and environmental challenges. So really starting to crack the door open for using generative AI methods towards quantum computing. So the next success story I want to talk about is work that we did with BASF. So they are, of course, a large chemicals company. And what we did was actually simulate a chelating agent, which is essentially a molecule that binds to metal ions. So this is very important for things like detecting toxic concentrations of waste metals within your water supply, or also detecting concentrations of toxic materials within the human body. So what we were able to do is use an approximate tensor network method using matrix product states and simulate a 60-qubit simulation of a molecule called FENTA. This was a hybrid algorithm using QuantumQ. We ran this on our internal AOS H100 supercomputer. Some of this work was also done on Perlmutter at NERSC. But what this let us do is to start to probe kind of a scientific regime that is really difficult to probe with conventional simulation or techniques or with quantum processors today. This is a pretty difficult problem to simulate. So what we're able to do is get convergent results for the 60-qubit MPS method, and it's one of the largest simulations of its kind. So really starting to push the envelope of what's possible through simulation and to understand some really interesting novel techniques. This third use case that I want to talk about is work that we did with HPE Labs. So what we're doing here is actually simulating a 2D dynamic quantum phase transition. So this is a pretty heavy-duty condensed matter physics problem where we're simulating a highly entangled transverse Ising model Hamiltonian. So this is a full state vector simulation, meaning we're simulating essentially all of the information within the quantum system, and we're evolving that in time. And it's a very, very entangled system. So this is a 40-qubit simulation where it's a noiseless simulation, so we have perfect information of what's happening to the dynamics of each particle within the system. And what we're able to do is find where this dynamic phase transition actually happens in time. So this is really important for the design of new materials in the future. Applications within the space include designing things like new quantum sensors. So if you park a material near its phase transition, this gives you a very, very sensitive quantum sensor. This is a very difficult problem to simulate. So what we found is we've gotten about a 600x speed up using CUDA Quantum and A100 GPUs. This is done on Perlmutter as well. And compared to a CPU simulation, we estimate that this would have taken about 7 years to run on a CPU, but ran in less than an hour on Perlmutter. So really, really fantastic results. I really start to understand where these kind of dynamic phase transitions start to happen. And really leveraging the GPU infrastructure to get really good results that run under an hour. This final example that I want to show is work done by JPMorgan Chase and Argonne National Labs. So they've developed a very, very fast simulator for simulating the quantum approximate optimization algorithm. So this algorithm is very useful for kind of heuristic optimization methods, for example, for things like portfolio optimization, other financial optimizations, things within that flavor. And what they were able to do is integrate QQuantum, which is our SDK for accelerating quantum circuit simulation, and run this problem at supercomputing scale, do some scaling studies, and actually find that there is a numerical advantage to using QAOA for these specific types of financial applications. So this is really important because these are difficult simulations to run. You have to scale out the size of your simulation incrementally to kind of understand how the problem scales as you increase the problem size. And they're actually able to find a numerical advantage, which is really, really awesome. Okay, so let me switch gears now and talk a little bit just about our platform. Please stay tuned tomorrow for Efrat Shabtai's talk on getting started with CUDA Quantum. But I just want to give kind of a high-level overview of some of the tools that you'll have available to use for QHack. So CUDA Quantum is, of course, our platform for hybrid quantum classical algorithms and application development. It's a single-source C++ and Pythonic programming model. And includes a high-performance compiler for hybrid CPU, GPU, and quantum processor systems. It's quantum processor agnostic. We have a lot of quantum hardware partners today that have integrated CUDA Quantum into their software stack already, and we're working with many more to integrate into their systems. And it's interoperable with leading scientific computing and AI tools. So like I said before, this is the platform that we use for the GPT quantum eigensolver work and some of the other examples that I mentioned previously. Just to give you a quick flavor of the performance that you can get, it contains a very fast compiler. So for things like a single BQE iteration, this is a quantum chemistry problem. As you increase the number of qubits in the system, the synthesis time and the compilation time actually starts to matter. So there's a GPU to GPU comparison where we're comparing QAL-TNO running a single iteration of this problem compared to another Pythonic framework, and we're getting a very substantial speed up from the compilation stack. I'll just mention that QAL-TNO 0.6 is now available. It's recently available as of I think a couple of weeks ago, so definitely check out the new features. And I want to talk a little bit about QQuantum, which is our SDK for accelerating these simulations using GPUs. So underneath the hood of QQuantum, QQuantum is actually providing the acceleration libraries for running the quantum circuit simulations on GPU and providing these hefty speedups that we're seeing when we simulate these systems. So you can simulate ideal or noisy qubits with state vector tensor network methods. I referenced our tensor network library before in our BASF work. And it actually supports GPU supercomputing with multi-node and multi-GPU circuit simulation functionality. So as an end user, if you want to scale out the size of the problem that you're addressing, you don't really need to worry about that. We provide the APIs and all the functionality for that to happen underneath the hood. So it makes it very simple to run these simulations at scale. And just to give you a quick flavor of the speed and the performance of QQuantum, I'm showing a couple of different quantum algorithms here and running them on different numbers of GPUs. As we increase the number of GPUs used for these simulations, you see a pretty substantial speed up in performance of the simulation. So the fastest one here is Shor's algorithm running on 8 H100 GPUs. And we're seeing about almost a 400x increase in performance compared to a pretty hefty CPU system. So just really fast performance here. It really will increase the throughput of your research and iterations of any sort of algorithm or application development. The last slide I want to show here is results from our tensor network library, QTensorNet. So what we were able to do a couple of years ago is just simulate a massive system for solving a max cut problem. We were able to simulate 5,000 qubits on 20 nodes of a DGX A100 system and get very good accuracy results. So tensor network methods are fantastic for looking at systems at scale, depending on the application, depending on the depth of the circuit. But it's a really, really useful complementary tool to simulate large quantum systems, depending on the application. Okay, I think that basically brings me to time. So I want to thank you for your time. Hope that was useful for giving you a flavor of what our platform has helped enable. And I definitely want to encourage you to tune into Efrat Shabtai's talk tomorrow. She's our PM for QAquantum. And she'll have a really, really nice demonstration of how to get started with QAquantum for your own applications and for your own projects in QHack.
All right. Thanks so much, Jin-Sung. That was really interesting, actually. Thanks so much. We have a lot of questions, so I'm going to try and zoom through as many as I can. But if your question doesn't get answered here, guys, go to the Discord. Jin-Sung will be there, and any questions that didn't get answered, you can ask there. All right. So we have a question from Mega Make on Twitch. Does the platform provide a common quantum programming language like CUDA shader languages, or support standard open source QPL like Qiskit?
Yeah, so the programming environment is very similar to essentially all the other ones that you're probably already familiar with. So you basically allocate qubits, you apply gates, you do readout, you ask to sample the circuit. There's also higher level libraries, but if you're familiar with things like Qiskit or Cirq or Penny-Lane, the programming environment looks very similar to that.
Cool.
Kind of underneath the hood, so QAquantum is open source. We also compile down to an intermediate representation called the QIR, which is how we actually interact with our quantum hardware partners.
Cool. Okay. Hopefully that answers your question, Mega Meg. Just a comment from Entiato. Thanks, man. Awesome presentation. Another question from Dentucky Kirby. Quite a bit of compilation flavored talks this QHack. Is this what you think companies are trying to shift towards programming wise? Like, should I learn LLVM instead of being a Python ninja? Lol.
So you can if you want. It's important. It's an important problem. If you want to be, if you want to just program in Python, you can do that with CUDA Quantum, and it'll just compile down to LLVM. And as a user, you don't really need to worry about that. But if that's something that you're interested in, it's open source, so you can also start to tinker around with the compiler stack within CUDA Quantum.
Cool. All right. There's a lot more questions we didn't get to, so yeah, definitely go on the Discord, guys, and ask them there. Thanks so much again, Jin-Sung, for your time and your presentation. Really appreciate it. And for everybody here, definitely check out Efrat's talk tomorrow for getting started with CUDA Quantum. That's on Friday at 1 p.m. Eastern time. Thanks again, Jin-Sung, and chat soon. Cheers.
All right. Thanks a lot.
All righty. So we have another talk coming up from Misty at Unitary Fund. So stay tuned for that. We're going to take a quick break here. Don't go anywhere. Maybe get some coffee or water, but don't go anywhere. Leave the stream open, and we'll be back shortly with some stuff from Unitary Fund. All right, everybody. Sorry about that. We're back here with Misty. Misty is from Unitary Fund. She's a member of the technical staff there. She's a lead developer of the quantum error mitigation software package, MITEC. I can't remember how to pronounce that. And a researcher in quantum error correction, or quantum error mitigation. Excuse me. Let's all give a warm welcome to Misty from Unitary Fund. Misty, how's it going?
Great to be here. Yeah, thanks for inviting me.
Our pleasure. You're from San Jose, or you're coming to us from San Jose, another Californian, where the weather's beautiful, and it's just absolutely getting more miserable here by the second in Toronto. So very jealous. But anyway, take it away, Misty. You're going to talk to us about Unitary Fund.
Yeah, thanks for the introduction. So yeah, I want to share a bit with you about the organization I work for, Unitary Fund, and what we're doing to build up the quantum technology ecosystem. What we're doing for our community as a whole, and hopefully how some of you can get involved. So I'm sure you're having a great time with QHack. I hope so. And yeah, it's really exciting to see all of the participation and excitement around quantum technology. And so I want to share some of that with you from the Unitary Fund side. So like I mentioned, we're a nonprofit organization, and we are on a mission to create a quantum technology ecosystem that benefits the most people. And we want to expand the pool of people working on quantum technologies. We want to make the tools widely available and equitably distributed. So it's great to see students and enthusiasts and people from all different kinds of backgrounds coming together for this event. And we hope that many of you will want to continue to be involved with quantum technology in this really collaborative way. And so I want to share a bit about some of the main programs that we have at Unitary Fund. So the first one is our microgrant program, and that's for $4,000 that we give away for rapid projects in quantum technology. So get people who are excited about quantum technology and who are wanting to do something for the community that will benefit the ecosystem as a whole. So we help them do that with these microgrants. And I'll talk a little bit more about what that looks like in just a little bit. We also have open source projects, which the Unitary Fund team is kind of like the core drivers of, but we have lots of contributors from our community. So we have MITIC, which is a Python toolkit for quantum error mitigation. As Isaac mentioned, that's what I focus on at Unitary Fund. We also have a project called Metric, which is keeping track of the state of the art in quantum technology. So looking at benchmarks and kind of sourcing these benchmarks from the community. And then we also do a lot of events around quantum technology. We have a Discord. I'm sure many of you are familiar with the QHack Discord. Unitary Fund also has a Discord. We host the Q-tip project. We host events like our own hackathon, which is Unitary Hack, and I'll mention that in a little bit as well. And we run things like the Quantum Open Source Survey, which we just wrapped up the second iteration of last year. So this is our team. People from kind of a variety of backgrounds within quantum tech, and also community building and open source initiatives. Another thing that we have is our ambassador program. So these are people who've been contributing to our open source projects, who are passionate about quantum tech, and really making it a welcoming and inclusive place for people to join and learn more and get connected. And so we've been we've been doing that for a few years now, and really helping to enable and equip folks to then kind of build on their contributions and get more visibility within the community. We also have our grant winner community, and that's growing. We just last year had a convention for our grant winners, and they were able to connect with each other and learn from each other and even come up with some new ideas, hopefully, for future projects. And we have an advisory board that evaluates grant applications and advises grant winners, and really just helps our community with their expertise. And they come from a variety of backgrounds, a variety of industry, academia. So really great to have all of these different members at different levels of our community working together. And actually, one of our grant winners became an advisor on our advisory board. So you can also see the progression of people as they go through their career and through their quantum journey, getting more acquainted, not just with the technology, but with the people in the ecosystem. So a bit more about what the microgrants actually entail. So as I mentioned, they're $4,000 to fund rapid projects in quantum technology. And these are for explorers all over the world. You can apply at unitary.fund/grants. And so far, we've given out about 89 microgrants to recipients in 23 countries. So we really are doing this on a global scale. We've got our grant winners have successfully published some of their work. We've also, a lot of these are open source library projects. So, and then attracting additional contributors. Although we don't fund startups, a couple of startups have been spun out of projects that started out as microgrant projects, as well as a nonprofit organization, and that's QWorld. So definitely we've seen a lot of growth in the quantum community as a result of this program. And so we don't, these are no strings attached grants. We just want to fund people to do good work in building up the ecosystem. And you don't have to have specific qualifications. So we just say explorers in quantum. We just want to see that you have the expertise and the drive and the understanding to do what it is that you say you want to do in your application. And these are generally open source projects, but we've also had community building projects. We've had the PK project, people interested in quantum education. So a lot of different avenues and ways of approaching filling gaps in the quantum ecosystem that maybe haven't been addressed by industry or academia. We come in and we help explorers fill those gaps with our microgrant program. And the projects are usually 3 to 6 months in duration. And the application is very, very lightweight. It's just like a couple minutes and a couple minute video. And here are some projects that we've had in the past. So libraries, education programs, extending an existing library, benchmarking projects, and we feature these winners on our Unitary Fund YouTube channel. As I mentioned, we also host a lot of events for our community. So we have community calls on our Discord. We have them for our kind of team-driven projects like MITIC and Metric, but we also have things like for QTIP. We've hosted QIR in the past, Open QAOA. Yeah, we have a lot of people gathering on Discord in a variety of ways, on calls and channels and so forth. We also have Unitary Hack. And so that's coming again this spring. Been doing that for a few years now, and we get a lot of open source projects together. So if you like hackathons, I definitely encourage you to join Unitary Hack and work on exciting open issues and open source, and hopefully win some bounties by closing those issues successfully. We also sponsor the Open Source Software Survey, understanding more about our community and our community's needs, and also like kind of, who their roles, and kind of like what kinds of tools that they use and what kind of tools they're looking for. And yeah, an announcement about Unitary Hack is coming soon, not quite in time for this presentation, unfortunately. But yeah, it's fully virtual. We want people to contribute to projects they haven't contributed to before, or win prizes for contributing to projects that they're really excited about. Both are fine, but we do award cash bounties for closing issues. And we've seen a lot of growth in our participation. So we're really looking forward to this year's event. Another internally driven project that we have, but we encourage everyone to get involved, is Metric. So Metric is a platform for community-driven quantum computing benchmarks. And so this is kind of like Papers with Code, if you've heard of that, but it's for quantum technology. So understanding what is the state of the art for various benchmarks in quantum computing. And so anyone can make a submission in Metric, and the way it works is you put in a link to a paper, or you put in a data set if you've collected your own data, and you fill out some fields and you explain what it's about. If it's somebody else's paper, of course, like you would put in like the archive link, and auto-populates a lot of things about like the authors and the abstract, things like that. But there are other ways to enter data in Metric as well. And then you get a nice chart like this. So you can actually, it's interactive. You can see the progress over time, and it helps people get a sense of where we're at and where we need to go in terms of quantum technology and how it's performing. The other internally driven project that we have is MITIC. So MITIC is a Python toolkit for applying different error mitigation techniques. It is compatible with many front ends, including Penny Lane, and it's designed to be backend independent. So you can have a simulator, you can have real hardware of pretty much any provider, and as long as you can interface to it properly from your front end, MITIC can apply error mitigation on your quantum program, your circuit, and help you get better results. And so we have a variety of techniques that are pretty well known in error mitigation, like zero noise extrapolation and probabilistic error cancellation, and we're working on adding more. And so I will I know we're getting close to the conclusion, so I will just kind of flash through these, but you can kind of see how MITIC can take a quantum program and change that into multiple quantum programs, instances, execute that on a backend, and then perform some inference on the noisy results. And just a visual representation of some of the techniques that we have in MITIC: C&E, PEC, learning-based methods, symmetry-based techniques, digital dynamical decoupling. So we have quite a variety, and we encourage people who are interested in contributing to quantum software to try MITIC out and to consider contributing to it. And that brings me to some FAQs about open source, because that's a big part of what we do at Unitary Fund. So why should you contribute? Well, you can make a difference. You can make a difference in the quantum tech ecosystem You can also expand your contributions beyond the quantum tech ecosystem, and you can bring something of value that other people can use and can build on. You can also advance your career. That's how I got started in quantum technology, was by contributing to MITIC, and eventually became technical staff at Unitary Fund. So I know this very well, that you can really build a career through your open source contributions if that's what you really want to do. And it's fun. You meet a lot of new people, you exchange ideas, and you learn a lot. And you can contribute a lot of different things. You can contribute code, infrastructure, things on GitHub. Documentation is very important. Penny Lane has great docs. MITIC, we try to do that as well. But also user interface, user experience design, data is very important. You saw that with Metric and the benchmarking platform. User feedback. This is also a very important one. So it's not just code, there's a lot that you can do in the open source community. And yeah, there's a number of different ways to get started. So you can find a project on GitHub, you can join a community on Discord, like the one we have at Unitary Fund, or the QHack one, and you can join a hackathon, which you have. And hopefully we'll also see you at Unitary Hack. So stay tuned for our announcement about that. So just to conclude, I would say open source communities continue to add value to the quantum tech ecosystem, and your contributions can help them grow. So wherever you may be in your quantum journey, your contributions count. And I hope you connect with us at Unitary Fund. Thank you for your attention.
Thanks so much, Misty. That was really nice. I gotta say, I'll leave this slide up for a bit, actually, for people who want to note all this stuff down. Really like Unitary Fund, like the whole philosophy of the whole thing. I think it's really awesome. We have time for one question. We have a question from Quantum Learn on Twitch. Misty, how did you get involved in Unitary Fund?
Yeah, so I actually got involved in 2021 with the inaugural Unitary Hack. And I made my first contribution to MITIC during that competition. And I was just really impressed with even just the interactions like on GitHub and Discord. And I wanted to stick around. I knew I wanted to kind of make a career pivot into quantum technology that way. And so I thought, yeah, maybe open source is the way to do that. And so I just kept building up my contributions to MITIC, getting to know the team, learning about error mitigation. And yeah, eventually, just 2 years ago, I joined the team. So yeah.
Nice. Cool. So through Unitary Hack, there you go. So humble beginnings for sure. All right. So there were some more questions, but for those of you who didn't get an answer, go ahead on the Discord. Misty will be there shortly. We have to say goodbye here, Misty, but thanks so much for joining. We really appreciate it, and hope you enjoy the rest of QHack. And we'll see you guys at Unitary Hack. I'm sure we'll be involved. I think we already are, actually. So yeah. Great. Cheers. Have a great rest of your day.
Thank you for having me. Thank you.
Bye. Alrighty, everybody. So next up, we have Marco from University of Sherbrooke. He's going to talk to us about scaling quantum optimization applications using NISQ systems. So you don't want to miss that. So stick around here. We'll be back in about 8 minutes right at 2 o'clock. Yeah, we'll hear from Marco from University of Sherbrooke. Cheers. All right, welcome back, everybody. We have another talk lined up from Marco from University of Sherbrooke. Marco has a PhD in mathematics from the Université de Montpellier in France. Oh my gosh, my French and English there just had a little meet in France. After this, he went to Sherbrooke to do a postdoc on the mathematics of deep learning. So let's welcome Marco. Marco, how are you doing today? Hello, bonjour.
Hello, thank you. I'm doing really good. Yes, and I've been doing quantum computing for the last 3 years. And that's exactly what I'm going to talk to you about today. This was a joint project with Lockheed Martin. And for legal reasons, I can only tell you what I did in this project, but I can assure you it's pretty interesting. So it's scaling quantum optimization applications, meaning that we will work with QAOA. If you haven't heard of it, I'll introduce the important parts of it during the talk. And we want to scale it as much as we can. And we want to use the NISC devices. That's basically the whole idea. Well, in the Algo Lab, so I'm a quantum software developer at the Algo Lab at the Institut quantique at the University of Sherbrooke. And we are having our Algo Lab summer school on near-term quantum algorithms. So if you want to log in, register, here's the QR code. You can just Google it too, the Quantum Algo Lab Summer School. And you can join us from June 2nd to 14th. And it's going to be in Juvence, Quebec. So take a note. Okay, so just a quick introduction to what we want to do here is we have some gates. And these gates are produced by electrical pulses on the machines on superconducting quantum computers. And this takes a certain amount of time. And there are two sets of gates that we're interested. One is the swap gate, and the other one is the RCC gate. This is a parameterized gate, and it depends on a parameter theta. And what we would like is to take these electrical pulses and make them shorter by doing some optimization. So this now measured in nanoseconds. Now, the dt has to do with how the device measures its units of time, but translated to nanoseconds, it's in these numbers. So the swap gate is 1200 nanoseconds, and the RCC gate is like 800 nanoseconds. And we want to reduce this. And the idea is that these two gates appear a lot in this QAOA algorithm. This algorithm it comes in the form of layers, and it's a hybrid algorithm, meaning that it runs, some parts of it run on the quantum device and other parts run on a classical device, and you need this classical quantum loop to train it. And so this is the part that runs on the classical device. And these two gates, the RCC and the swap gates, these are repeated a lot of times inside the inner layers of QAOA. And the part that we want to scale is the depth of QAOA, because there is a theorem that says that the QAOA circuit can express the optimal solution to the combinatorial optimization problem when the length of these layers goes to infinity. So we cannot do this like for a high number, but what we want to do is we want to be able to do these gates in a shorter amount of time. Well, inside the QAOA circuit, for instance, this is one small example for 3 qubits. And we start with the superpositions, and there are two pieces of the QAOA circuit that are very important. One is called the problem Hamiltonian. It comes from the problem Hamiltonian, and it depends on the problem graph. So since we're doing combinatorial optimization, this problem comes encoded in the form of a graph. And sometimes, and there's a mixer Hamiltonian that is important for other things, like to prove this theorem that you need. And these swap gates, they appear because the physical device, like you may use the physical qubits on the device, but they may not be connected as those on your problem graph. For instance, if your physical device is like this, there's no connection between 0 and 2, which means that you have to swap either qubit 0 and 1 or qubit 1 and 2, so that 0 and 2 are close to each other for you to apply the next gate that involves these two qubits. And then you need to take back these two to its own place. So this makes it a little bit more complicated. You have more complicated graphs, and actually on the quantum systems, we have the connections are not that complex, so you really need to do a lot of swaps to get arbitrary graphs. And in these cases, it's like this. Now for 65 qubits, now there's no more 65 qubits devices, but for 127 is like this. So, and you will have like to deform this graph using swap gates, and you will need a lot. So you need a lot of swap gates if you really want to make QAUA useful. Okay, now in the physical device, we have a way to look at the Hamiltonian of this object. And in terms of quantum mechanics, what that means is that if we understand the Hamiltonian, we can control this quantum system, and we know the outputs that it will give us, and so on and so forth. Now, what you can see here on the screen is 2 qubits connected by a capacitor, and each one has its own how do you call it, like a pulse that you send to it to change its quantum state. Now, each part of this diagram has its own Hamiltonian. This part here, I will call it the part of the qubit 1, and its Hamiltonian comes in the form of HQ1. Same thing for the other part. This is the second qubit, but we also have the Hamiltonians for each one of the pulses. The pulse that is being sent to Q1 and the pulse that is sent to Q2. And there's also one part here in the Hamiltonian that represents the connection between these two qubits, between these two systems. And this is controlled by a parameter J. Now, why do we care about this? Because we would like to do pulse optimization. Now, pulse optimization means you're gonna take a pulse and you're gonna reshape it so that it gives you the right output that you want. And since you want the way that you measure if you have the output that you want is by using the Hamiltonian of the system. So in Open Pulse from Qiskit, this allows you to play around with pulses and send custom pulses. And so the equations look kind of like this. Now I could tell you how each one of these equations relate and how you work around the optimization, but it's pretty simple. Like you just need to follow the chain rule when you do derivatives, and it tells you how to follow the gradient in this case. It's actually gradient ascent because the cost function, it has a minus sign somewhere. Now, there are some limitations, and is that not all the coefficients of the Hamiltonian of the physical device are known. So, for instance, in this expression, for HQ1 and HQ2, each one has the two factors that are the Josephson energy and for each one of the qubits, but also this J, which is the coupling between the two qubits. This is not known, and you have to do it by experiments. So some of these values, they can be determined by these experiments. Now, by sending pulses with different shapes and different sizes, you can get curves. Then you do a curve fitting, and that gives you one of the parameters. And then you can do this a couple of times to get a pretty good approximation of the actual Hamiltonian of the system. And once you do that, you need to do the optimization, and this is called GRADE. And it's the letters for gradient ascent pulse optimization, pulse engineering. And what you do is, given the Hamiltonian of the system, which we already have because we did all these experiments. Now, of course, this Hamiltonian will be simulated, so it will still be a simulation of the approximation of the actual Hamiltonian. Now, you initialize a random pulse, and then you make discretizations on this pulse. And this is one of the parameters that you have to tune when you do these optimizations. And what you do is you compute the gradient with respect to the height of each one of these discretizations on the pulse. And then you follow the gradient, and that gives you a shaping of the pulse during the optimization. Yes, and we want to minimize leakage. This means that the information is going, since these are transmon qubits, you may have leakage to higher energy levels. You want to minimize that. You want to keep on the first two energy levels of your qubit. But also you want to maximize gate fidelity, meaning that you did the actual computation that you wanted to do in the quantum system. Okay, now for the case of the swap gate, we did this. Now, currently, if you do a swap gate, this means you're applying 3 CNOTs, and this gives you 1200 nanoseconds. Now, after running a couple of optimizations and getting the optimal one of those, we found one with 320 nanoseconds. Now, this pulse makes the same operation, and it minimizes leakage and it maximizes gate fidelity. Okay, and so this means we've seen an improvement of 73% on the length of the swap gate. Now, this other gate, this RCC gate, this is a parameterized gate. So for a given parameter, what we have is that right now you need, in terms of nanoseconds, this is 800 nanoseconds, and we found another one with 320 nanoseconds that does the same operation. And this means we have an improvement of 60%. And what we did is, since this parameterized gate needs to produce a pulse for every theta, and this theta will be optimized during the QAOA optimization. That means that for any theta, we should be able to produce a pulse. And that looks like a task for a neural network, for an AI. And that's what we did. So basically, we ran a lot of samples for this optimization on grade, and we created a data set of 100,000 angles between 0 and 2 pi. Then we produced for each one of the angles, we produced a pulse schedule that corresponds to the gate on this specific angle. So that's why we use a lot of GPU hours, because we did a lot of trainings. Yes, so in this case, what you see is, here you see 8 crests, and that's because each qubit, the way we engineer the pulses, each qubit receives 2 pulses, and each pulse is complex. So that's why you see 8 here, because each qubit receives 2 pulses, and each one has its real and imaginary part. So the first crest is the real part of the first pulse, second part is the imaginary part of the first pulse, and so on and so forth. And here in red, this is the ground truth, the pulse that was optimized, that we know that gives us the operation we want. And the blue one is the predicted by the trained neural network. Now, the way we partition the data here on the left gives us some big errors between the crests. So we started doing it we gave it other approaches. So we optimized like crest by crest, but this we have to optimize a neural network per crest, but still it can be done. And the approximation is better in this case. And now I think this is a video. Yeah, okay, so what we did is, we did a PCA on the data set of pulses, and then we learned the principal components only. So, and what you see here is the learning at different epochs, how the prediction evolves. It should stabilize somewhere. Yes. So as you can see, it's not better, and it stays like this, like for the next 100 epochs, I guess. But that's the idea. The idea was to use neural networks to help us build these pulses. And what we said was okay, let's try this on one pulse, like one complex pulse, and then look at the measurement outcomes of the differences between the prediction of the neural network and the pulse that we already optimized. And what happened was it looks good. So to measure like the zero state, when you send, what we did is, the experimental setup is, you have the zero state, you send the pulse from the grade optimization, and then you measure the probabilities of getting 0 or 1. And we got these 2 values. But for the pulse on the neural network, you can see that the difference is very small, and that gives us like 10% difference but this is just for one pulse on one of the qubits on this big circuit that we wanted to approximate. So the outcome of all of this is that you should do better optimizations. After finishing this project, we started working with the loss function. Now the loss function of the neural network, and this also comes from a paper. I don't remember the authors, but someone already did this. Is putting the Hamiltonian directly in the loss function of the neural network, and that helps learn the pulses better. So that's it. Thank you very much.
All right, Marco, thanks so much. That was really interesting. I have to say, I'm a sucker for a good acronym. GRAPE is awesome. One of the first packages that I ever was a part of in grad school was called Cucumber. It was basically just like the acronym is horrible. It's a huge reach, but it was a package for restricted Boltzmann machines for like classical machine learning. Anyway, I'm a sucker for a good acronym, so that was good. Okay, so we have a couple questions from the chat. I think this had to do with an earlier slide in your presentation. This one's from Quantum Catalina. Would this work on any quantum device or just a specific one? So I think this is just in relation to something that you showed in your first few slides. Maybe we can go back to that.
Which one?
Yeah. Okay. Maybe we can come back to this question. Actually, if Quantum Catalina wants to clarify there, we can continue.
Okay.
I think it's this, but yeah, let's just wait for Catalina to clarify. Another question from.
Oh, I can just.
Sorry. Go ahead.
Oh, yeah. So this is for any superconducting quantum computer, and in particular, IBM does it like this.
Right.
And this circuit, this is called circuit quantum electrodynamics, and everyone that is doing superconducting qubits, it's doing something like this. So the mathematics of this that I showed you, how to get the Hamiltonian, how to produce the experiments that give you the values on the Hamiltonian, that you can reproduce it on any machine that is superconducting, that uses superconducting qubits. And also the QAUA algorithm, this is gate-based, so that also another thing that to keep in mind. But in principle, yes, this whole pipeline can be reproduced in any superconducting machine.
Yeah, and Catalina actually clarified in the chat, so that answered the question. So thank you. Another question from Broken Symmetries: how do you find the sweet spot between maximizing fidelity and minimizing leakage?
You don't. You compromise from the beginning. So basically, what we did is we constructed a loss function, a cost function that has 1/2 for the minimization of the leakage and 1/2 for the how do you say, which one was it? The one is minimization of the leakage, and the other one is maximization of gate fidelity.
Yeah. Yes.
So you put it 1/2 and 1/2, and then it reaches 0. So that means that both are 0.
I see. Okay. Another question from Andresulid. In general, pulse scaling is done for 2-qubit gates. The idea is to try to reduce the rotation angle generating the same effect.
Say again.
Yeah, I'll try and read that again. In general, pulse scaling is done for 2-qubit gates. Is the idea trying to reduce the rotation angle generating the same effect?
Not the rotation angle, the length of the pulse.
The length of the pulse.
Yes.
Okay.
Which is different. They may be related, but not in general.
Okay. All right. So that's the time that we have. But if there are any more questions for Marco, Marco, you'll be on the Discord shortly after your talk. So thank you for that. Everybody, let's give one more thank you to Marco, and thanks again, Marco, for your talk. And cheers. Have a great rest of your day.
Thank you.
All right. Cheers. Okay, we have another talk coming up from Valentin Senicourt from Sandbox. They're going to talk about Tangelo, an open source package for quantum chemistry simulations on quantum computers. Another fruit-based acronym, probably, of quantum software package. I love it. Keep them coming. We'll be back in about 10 minutes. All right, everybody, welcome back. We have a really exciting talk next. We have Valentin from Sandbox coming. Valentin is a staff research scientist at SandboxAQ and was previously the quantum software lead at Good Chemistry. He leads the development of Tangelo, which is an open source Python package for end-to-end chemistry simulation on quantum computers. So we're here to talk about Tangelo today. So Tangelo, I got your name and the software package mixed up. Valentin, welcome. Excited to hear your talk today about Tangelo.
Yeah, me too. All right, shall we get started?
Yeah, go right ahead. Floor is yours.
All right, everyone. Well, thanks for coming. I hope you're having a great time at QHack. Must be really fun. Today, we're going to talk about quantum chemistry workflows on quantum computers. On today's menu, first, we're going to go over an overview of what Tangelo is, and then we're going to explore a little bit all the online resources that are available. They are mostly on GitHub. We're going to do a little demo just so that you can see it in action and not get bored by just slides and me talking about it. And then eventually we'll just wrap up. So first, for an overview, what is Tangelo? Right now, in the field of quantum chemistry, we can't just take a molecule and just throw it at a quantum computer and get something nice, reliable, and useful from it. We have to be a bit smarter than that. It's a bit more complicated. We have to kind of build entire workflow to massage like these chemical problems to make them more amenable with quantum exploration, with simulators or with devices. And that's really with that approach in mind that as a group researching chemistry and wanted to apply quantum computing to it, that we approach our work with Tangelo and our R&D. From the definition of a molecular system to picking an algorithm to eventually taking it to one of the many awesome quantum circuit simulator or quantum devices, and eventually post-processing the results and repeating that until you get something meaningful. Tangelo is an open source Python package with very permissive license, so it plays well with the whole Python ecosystem and many exciting projects around. And really the goal was to accelerate the R&D and the learning on quantum computing in the field of quantum chemistry, focus on experiments, and make the most of it to accelerate R&D. And that was really central, is that when we came up with Tangelo, we really wanted to come up with an engine to accelerate research. There were many tools around, but they were not quite fitting the bill, and we decided to implement our own approach. Two big things for us was to do quantum algorithm R&D, to easily prototype new approaches and compare it with existing ones from the perspective of the accuracy, like how accurate in terms of quantities that are relevant for chemistry approaches are, or in terms of resource requirements, how many gate, how many qubits, how many measurement, how close they are to quantum technologies and their capabilities. And the other one really is that we wanted to do hardware experiments. We wanted to play with these nascent quantum devices that are proliferating in a positive way, and to stay connected to the development of the technology to essentially understand, okay, how far, how close are we to leverage these powerful devices to do something meaningful in chemistry, or to at least better understand how they work. And again, this is an engine to accelerate research, so we wanted to make sure that essential steps in learning and research were covered. That is, we wanted to build something that really helped us prototyping new approaches, reproducing all of the amazing research that is being published almost every day, benchmark different approaches and compare them, procure our own innovation or let people innovate in general, but of course integrate this innovation back into the software so that we can keep this virtuous cycle going. So that's really the philosophy, I think, behind Tangelo. Now, what does it look like? Well, basically, the idea of Tangelo is that we wanted to take chemistry to any quantum platform. For us, that was a requirement. If we wanted to do good chemistry, if we wanted to leverage all of these cool technologies that was emerging, we had to kind of develop a library of toolboxes and algorithms that allow us to take interesting chemistry problems and then build something that could run on, these many devices and simulators to study chemical system. On the top of this slide, you have a layer that is what I call the application layer. That is mostly about chemistry or about toolboxes that do not need to know what hardware or what simulator is being used to simulate or execute a circuit. In blue, you have basic toolboxes that contain functioning classes that are fundamental building blocks. For example, we have some to help us map a molecule to qubits. We have some toolboxes to post-process results that come from outside a quantum device to kind of like increase the accuracy of a result, deal with noise, or reconstruct quantities of interest. And then we have toolbox for molecular computations. We have toolbox to help you design a measurement strategy. It's very varied, and there's so much more. Then we have another kind of bigger building block. We have entire algorithms in there. It's not just variational approaches, even though like people are very excited about VQE, there's so much more. We don't discriminate between NISQ or fault tolerance. There's classical solvers in there to help you get reference results. And in fault tolerant, you have algorithms around phase estimation, imaginary time evolution, everything that has to do with Hamiltonian or time evolution, and much more. And on top of that, you have another building block that we call problem decomposition. In our work, we always wanted to make sure that we could tackle systems that go beyond toy models, beyond the H2 or the lithium hydride that everyone starts running experiment on. We're going to talk a bit more about these techniques, but essentially they can help you scale to study what quantum computers could do as part of more, let's say, industrially relevant problems. On the bottom layer, we have everything that has to do with what I call compute backends. So we can connect all of these building blocks or these algorithms to cool simulators developed by the community, some developed by us. You can see a few names that you know already, as well as quantum devices developed by, I don't know, like a number of big players and smaller players. And last but not least, you can also define your own custom backend. If you define how, for example, a quantum circuit is simulated with your own code, regardless of what that code is doing, or how to compute an expectation value, you can kind of plug that into algorithms to decide how they run. That was a lot of information right now. So we're going to see in the next slides what it looks like. This overview doesn't look too much at code, but we'll jump in a bit later into it. What was really important is that we have a tremendous ecosystem around quantum and its application. And we believe that if you want to do good research in that field, you should be able to harness all this innovation that's scattered across the instrument. You should be able to leverage all of them together. And in the design of Tangelo, we wanted to make sure that, for example, key quantum quantities like operators or circuit were easy to translate, to build bridges between all of these different frameworks, and to make that as simple as possible for you. So on the bottom right, for example, you can see a glimpse of what these translation functions look like that just take a target and a source format, and you're pretty much done. And the goal of that is that we don't want people to spend too much time on APIs and connecting the software they need if they're not interested in that. They can focus on the high level. The big question: how do you want to approach this chemical simulation and the modeling? For example, what kind of algorithm and strategies do you want to use? What kind of quantum algorithm do you want to apply, study, compare? And finally, at the high level, well, how do you want to simulate or execute that circuit? Do you want to use a particular simulator or device? Do you want to use shots? Do you want to use a noise model? And the goal of that is really, you want to spend less time on the nitty-gritty sometimes, and you want to be at the high level and be more in command of really what you're trying to achieve on the science. And you want to leverage all these tools together. That being said, convenience is great, but fine control is important for experts and researchers. So at the end of the day, you can always go down essentially with toolboxes and kind of explicit everything yourself. You're not tied with this high-level abstraction that we provide. Earlier, I mentioned problem decomposition. And for us, that's something we've been interested since our early days at Good Chemistry, or even 1QBit before that as the chemistry division. We believe that in order to do interesting things in chemistry, it's important to leverage what the field of chemistry has figured out in order to scale to larger molecules and bigger problems. We have an array of what we call problem decomposition or fragmentation techniques that can be useful for different fields, such as battery chemistry, discovering new functional material, or biochemistry. You can see a few names of what these techniques are, and they're available in Tangelo. Chemistry is also about leveraging all the insight that we have about the problems. Chemists and physicists can predict in advance that in your system, in your molecule, in your electrons, for example, some of these electrons are not going to contribute meaningfully to the problem. So instead of just trying to force the entire molecule essentially to a quantum computer, well, you can be smart and know in advance that there are parts you can cut off to reduce the complexity. And what does that mean? Well, it means you can look at bigger problems. It means you can do more with a restricted, quantum device or the simulators that we have today. And finally, on terms of mean field calculation for the modeling, you have a bunch of different things. I don't know how familiar everyone is with chemistry here, so I don't think I need to go into detail. Something interesting to mention is that we've also implemented in a different platform, because we've been always interested in chemistry, but we're not only doing quantum computing. This platform is called Chemist Cloud, and we implemented this method called incremental FCI, IFCI, that we scaled to essentially run up to 1 million cores in the cloud to tackle very hard problems that have to do with the biodegradation of what we call forever chemicals. So we essentially went to tackle a very hard problem with that. And there are blog posts available on AWS blogs. One is HPC related, which is this million core run I just talked about. But there's also another one to see how Tangelo and quantum computers can be paired with this decomposition IFCI to start to see what a quantum computer can do as part of a bigger, more scalable approach. We talk about algorithm, and I don't want to talk about VQE. Like, everyone is talking about VQE already, but I think it's a great example. We don't just simply implement algorithms. Our philosophy is that everything should be extendable, everything should be flexible, because we are merely a building block, and we always need to go further. If you're interested in playing with VQE, well, you should know that there's more, for example, that just Jordan Wigner and the Bravi Kitaev qubit mappings for mapping molecules. We have at least 5 of them in Tangelo, for example. People can provide their own Hamiltonian. If you're interested in playing with different ansatz for VQE, well, we got more than 10 already available, but you can also provide your own variational circuit and explore that. Same with the optimizer. You may want to control that. You can actually plug in anything. Any function, regardless of what library you use, can be here to dictate how the optimizer works. And finally, you should be able to plug in easily your different backend on your VQE. Do you want it to be noisy? Do you want it to be a particular type of simulator? Or do you want to define your own? Well, you should be able to do that. So here is just an example of a very strong philosophy in Tangelo that for every algorithm, for all these building blocks, we try to provide convenience. That is, people can just do things rather easily, but also fine control. If you want to tweak that thing and take it in a different direction, if you want to implement something new, something different, you have access to these building blocks and to easily modify things to do your own thing. And this is not the end. Again, VQE is just a building block. You don't want just an algorithm. All of the algorithms for us tend to track computational requirement. You have very easy ways to access how many gates, how many qubits, how many parameters, how many terms, for example, in VQE or other algorithm, the approach required to see if it's relevant or not. You always want to potentially extend them. For example, VQE has many flavors. You may have heard about adapt VQE, about the state average orbital optimized VQE, about the quantum qubit cluster. Like, essentially, all these algorithms are available in TANGELO, and they're built upon VQE. We keep building up. You can keep building up. And finally, we're building entire workflows, right? It's not just you can push any molecule into VQE and it's going to give you a result. You're going to be stuck with small molecules. It has its own challenges. So you should be able to combine them with other things. And for example, problem decomposition to look at bigger systems. And last but not least, hey, we want to do chemistry. So we want to make sure that we are able to look at interesting systems with the resources we have. So VQE, for example, here in TANGELO is compatible with open shell systems, compatible with active space selection to, again, trim the electrons and parts of the problem are not interested. You can study more than ground states. You can also look at excited states with VQE as well. So essentially, the bottom line is that it's not about just finding an algorithm and writing it. It's about building a framework that can take people further than that. And that's a strong philosophy in TANGELO. We talked about VQE, but essentially, you'll see it a bit later. We have a lot of building blocks around like fault-tolerant algorithms because we think that they are meaningful. Multi-control gates, block encoding, time evolution, measurement control gates, frameworks for algorithm like QP. If you're familiar with fault tolerant, you may have a lot of fun with TANGELO to try to build these new approaches. There's one thing that a lot of people don't talk about, and it's hardware experiments. We're very transparent. Actually, we usually disclose the entire hardware experiment process that we have in open source code and publications. And submitting circuits to a quantum computer is actually the easiest part of a quantum experiment. Like, there are big questions that come before and after that can take a lot of work, a lot of reflection, a lot of coding as well. The big questions you're trying to answer before running an experiment is whether or not the experiment is going to be within a budget. Because yes, you are working under constraints. Quantum computers are not a commodity, it's a scarce resource. And you're working either with a budget in terms of money or time on the machines, right? There's only so many circuits, there's only so many measurements you can take in order to collect data and hopefully do something interesting within and learn something. And the other question is, what is the likelihood of success? If I'm throwing all of these things at a device and I get noisy results, because currently devices are noisy, can I hope to actually extract meaningful information that make me learn something or that help me doing something for, I don't know, a publication and pushing the boundary a little bit? So before you run an experiment, you're trying to answer this question, and has to do, for example, with resource estimation. How many gates, how many qubits, how many measurements? Can you simulate the behavior of a noisy device to have an idea, okay, what's going to potentially come out of that thing? Is it just going to be noise and then there's nothing I can do? Can you simplify your circuits to maybe raise your chance? Can you define a better measurement strategy to try to make the most of your time in this device? And well, after you send all of these instructions, these operations to device, you get a bunch of histogram. Not the sexy one that you see on the right that has the bars and everything. Like, that one looks nice, but in reality, you're just juggling with a lot of numbers in all directions. And there's a lot of stuff you're going to have to do with that. You're going to try to aggregate them to recompute quantities of interest for your application. And maybe you're going to have to deal with noisy results. Maybe you're going to have to post-select some of them to renormalize, to map back these quantities to something of interest. Maybe you're going to have to remove ancillary qubits from all these histograms. Maybe you're going to have to resample this histogram. Maybe you're going to have to estimate the error bars. What is the expectation value? What is the variance associated with your experiment? And in there, you're going to throw maybe some chemistry inspired post-processing, because you're doing chemistry, so maybe you have some insights about what you should be doing. And it's interesting, I won't spoil too much about it, but last year, someone in our team ran an experiment that literally required thousands of quantum circuits. So we have applied this tool to go through volumes of data to try to extract the most information possible from what came out of a quantum computer, to learn something and to share it with the community. So hopefully in a few months, you see that coming out, keeps your eye peeled. But really, hardware experiments are tough. And well, we just need good tools to do that. All right, that's a lot of talking. I've been talking for like almost 20 minutes already, but you haven't seen much essentially of what we have to offer you, what you're gonna interact with. Let's get into the online resources in the GitHub, because most of the stuff is on GitHub. There's one big thing I just want you to remember is that Tangelo comes with a community and a lot of educational resources, a lot of tutorial, a lot of documentation, some blog posts, all with the idea that we're not just showing you how to code stuff in Tangelo, but these things are meant to help you understand with some hands-on as well, things about chemical modeling, how quantum algorithms work, and how hardware and hardware experiment works as well. So even if you're not using Tangelo, I think these are wonderful educational resources for you to dig a little bit into the topic, maybe look at the references and the articles and whatnot. Let's have a look, shall we? You should be able to right now see a web page. If you don't, someone please scream at me. This is the repo for Tangelo. It's still under Good Chemistry, but Good Chemistry has been acquired by Sandbox, so it will be moved soon, and this will have no repercussion on Tangelo users. This repository contains all the code, but it contains so much more than that. You have the usual installation instructions and everything. It's a Python package again, so you are free to install it directly with pip or from source from the GitHub as well. What's interesting with Tangelo is that it comes with a lot of resources. We have a vibrant ecosystem, and all these open source projects right the state of the art, so many features. We're trying to keep people up to date with simple visual. If you want to keep track of what's in Tangelo, you can just click, for example, here, and you see, stuff that's related to the quantum chemistry modeling, stuff that's related to the actual quantum algorithm, and stuff that's related to quantum devices, for example, which is a nice way to get, like, at a glance, the capability of what we have before you dig into it. And I think what's very interesting for you is that, well, we have an entire repository that's called Tangelo Example dedicated to examples and tutorials. And we have a large amount of tutorials, and we find that people have various interests. So what we started to do is we tagged all this tutorial. You can look at the tags here to see what things are talking about. You're interested in introductions, for example, you can just look at one of these introduction notebooks. You love variational algorithms, that here you go. There's 4 of them here tagged with VQA. You're interested in problem decomposition, you've got all the red ones. And if you want to read about actual hardware experiments that were run on various kinds of device, IBM, IonQ, or through Amazon Bracket, for example, well, you can have a look at that too. Pretty much every single topic we have discussed so far has at least one tutorial there, essentially, for you to explore. There's something very interesting too, I think, is that if you have a Gmail account, basically you can click this button, open with Colab, and you're able to get started right away without doing any sort of installation on your machine, and to explore some of the resources we have, some of these tutorials, but also some hands-on, essentially, that we've developed, which consist in a series of small exercises that people can go through and complete some code to learn about it. Here's, for example, a cool hands-on that coworker James Brown made about fault-tolerant building blocks. You're interested in fault-tolerant algorithms? Well, here we go. We just guide you with some essentially different steps and building blocks. We describe what control operations are, and we ask you to insert code to maybe solve small problems and everything. And we just keep going. You can learn about quantum phase estimation and how we can build it from scratch with all the building blocks in Tangelo, or simply directly reuse the framework and have an idea of how to interact with a quantum algorithm, passing options, building, simulating, and reconstructing key results. And it goes on with blocks encodings, amplitude amplification, like essentially you are very much guided. Whether or not you want to learn about simple topics or more complex one, there are resources in TensorFlow to help you achieve that. I'm going to close that. But the bottom line is we have a lot of educational resources from you, and whether you're a newcomer or a seasoned expert, we believe that TensorFlow can equip you to explore some of these topics. All righty. How about we do a little demo now? I've been talking about this for a while. It's a bit more concrete, but still not concrete enough. Here I'm taking an old story that we talked about in 2019. Back then, our team was part of 1QBit. And I want to show you how a few different functionalities can come together to give you an idea of the challenges that we face and how we try to tackle them. I clear-run this notebook just to get rid of all the installs and everything here.
Hey, Valentin, do you mind just zooming in just a little bit? I think it's, yeah.
Yes, I can. How's that?
Maybe a couple more.
A couple more.
There we go. That's perfect. There you go. Perfect.
That's very zoomed in. I hope most of the stuff is
perfect.
All right, fellows. Well, this is not very interesting here, but basically, TensorFlow can be easily installed from pip, and then all the dependencies, whether they are one of the many chemistry packages we leverage, PySCF, Cypher, RDKit, OpenMM. The open source community in chemistry, quantum chemistry, is also pretty rich. Or whether they are other tools you may have heard about developed by other people in the field of quantum computing. Let's have a look at this small use case, which is a ring of 10 hydrogen atoms. It's a very simple system. And in TensorFlow, it's fairly easy to just kind of read that in. If you just provide the coordinates of your atoms, you can build a molecule object. And if you print that object, you will see that many things have been computed about what we call the mean thing energy, how many electrons, how many atoms, how many orbitals in general, what kind of mean thing was computed, right? So you can access information in objects very transparently in general with TensorFlow. You work with quantum, but you always want to know where your approach sits in terms of accuracy compared with ground truth, or at least with the closest thing you have, which usually is classical simulation. So TensorFlow easily provides, for example, as algorithms, what we call solvers. Here's two classical ones that use classical computing to get some answer about the ground state energy of this molecule, which is the quantity we're going to be interested in here. If you try a good old approach with VQE, the vanilla one that everyone probably learns when they get started with what we call a UCC ansatz and maybe a qubit mapping that Jordan Wigner, here's how you do it with TensorFlow. You import this as an algorithm. You can use some of the built-in ansatz to say, I want UCCSD. You can just specify, I want Jordan Wigner. You push your molecule in, and you build an object. We separate the build from simulation because simulation can be really tough, really expensive, take a very long time. So before simulating, you may be interested in knowing what are the resources that my algorithm take, how complex it is. And at this very small problem, if you have a look for this VQE, you can see the number at the bottom. Wow. We see that we're in for a circuit that requires 20 qubits. That's the width. Okay, that sounds manageable for like simulators and whatnot. But you can see that the length of this circuit is like 30,000 gates. Right now, most gate model devices can maybe hold 10 or 20 of them before the results are drawn in noise. So clearly this approach is not going to give you anything on quantum hardware, even with infinite time. But even with this simulator, like we're trying to optimize parameters in a high dimensional space of size 350. This is a very big challenge for like an optimizer. If you have a fast and efficient like quantum circuit simulator, well, I'm not quite sure you're getting something out of this. And it's probably going to take a very long time to finish with your optimization, right? So the bottom line is that if you just try with vanilla, straight out of the box approach right now, you're most likely not able to study this system. And that's how, for example, tools such as problem decomposition can get in there. So earlier we mentioned DMET as one of these tools. What DMET can do is to really chop these molecules into what we call fragments, and then kind of compute quantities of interest on this fragment, and then remerge everything to get the answer to your original problem. So instead of solving a big hard problem that's out of reach, you're trying to solve a more or less equivalent collection of sub-problems that are a bit more tractable. The approach works just like for any other algorithm. You pass usually a dictionary of various options. I pass my molecule here, and you've seen my ring of hydrogen atom is very symmetrical. I'm going to basically ask the MET, can you aggressively chop this molecule into 10 fragments of 1 atom each? And because all these fragments in this particular case are the same, I'm just saying, okay, solve one of them with VQE, and you can solve all of them, the rest of them, sorry, with a classical, essentially, solver. And as well, I'm just building my object, and I'm just having a look at the resources, right? And we see something that is much more tractable. Suddenly, we find circuits that only have apparently 14 gates, right? And they only require 2 qubits for this particular fragments, and there's only 2 variational parameters to optimize. So suddenly, a problem that was just intractable becomes like much more tractable. If you want to look at the fragments, this is what you look like. This picture was made with another beautiful software from a chemistry ecosystem, just to represent what we're looking at here. With a simple call to simulate, I can basically do all the simulation. Here, everything would be done on a quantum simulator, and within a minute or so, we get an answer. When you can see what this approach yields. So we get a number, and I can compute the difference easily between this number and my reference value from earlier. So you get here something that's not quite at what we call chemical accuracy, but that's a result of the approximation made by DMET and made by applying VQE to calculate the energy of a fragment that eventually gives you the total energy of the system. So you get an idea of essentially how your entire workflow gets more or less close to the ideal value, the ground truth, or at least the best thing you have from it. Segue into that, great, you have run something on a simulator, but what if you want to explore that on a device or manipulate that further? Well, for example, here you can easily retrieve the information. You can retrieve that final optimized circuit with that simulator. And then if you want to go onto another framework, you're like, okay, I'm done with Tangelo. I want to move with like another framework. I want to take that to a quantum device, or I want to do my thing, right? You're welcome to. With just a simple call to here a translation function, you can get the equivalent Qiskit object. And then you can manipulate this Qiskit object just as easily as you manipulate Qiskit. You are effectively manipulating Qiskit. I think Qiskit does an amazing job at drawing circuits. I just love it. So here you go. Here's what the circuit, the optimized circuit that was obtained in the previous round with the VQE for this fragment looked like when we show it with Qiskit. And finally, it's very simple to send something to a quantum device. We have what we call QPU connections in Tangelo that are essentially simple interfaces that connect you with all of these services. We don't do any magic, as much as I would like it to look like magic. In reality, we use the open source toolkits and interface provided by Amazon, by IBM, by IonQ, you name it, and we just make it as easily as possible for you to use. For example, here, I think the runtime probably has disconnected. What if I try to run this again? Am I going to get an error? No, I'm not. Here's what I'm doing here. I'm going to essentially throw a quantum circuit at a device or a simulator, because I don't want to wait. A device would put me in a queue, available on IBM Quantum. So I'm importing a class called IBM Connection. I'm using a personal token. You cannot see it fully because I have an account on IBM Quantum. Everyone can create an account, by the way, on this platform. Then I'm going to instantiate my IBM Connection, and I'm simply going to call the job submit function. I'm going to tell essentially what kind of job I want. Here, I want to simply look at my circuit from earlier, the one that I showed you, and I want to run it on a simulator with 1,000 shots, and I just want to essentially sample that circuit, right? And here I can provide some additional options, all in the style of what IBM done. I can query the job status. It's printed below. It was telling me that the job was running. And finally, I can get my result. And as you can see, we have an histogram. This is my personal account on the IBM Quantum platform. If I refresh this page, you will see that, there you go. I just ran a job 1 minute ago. So what you see here is me interacting live with that platform. Of course, if you pick an actual device, you're going to be put in a queue. It may take several hours for your job to complete and everything, which is why here I just use a simulator, but it doesn't take much more effort to do that. With that, I hope I gave you an idea of how all of these toolboxes come together for you to do interesting research around quantum chemistry with quantum computers. I have a bit more time, and I want to give you just a quick example of how. Let me skip to this slide quickly. There is no better validation than having people from your community and your colleague telling you about success stories. And if you remember, one of the big things about Tangelo is that it was designed to be an engine to accelerate research. And there was a few key steps in research that we wanted to be very efficient. There was this article found by my colleague Alexandre about GraphQC, which kind of implements like a graph decomposition techniques on molecule, essentially to decide how to decompose it, and then use the problem decomposition technique and the variational quantum eigensolver to compute quantities of interest, like the ground state energy, again, because the community has been very interested in that problem. And Alexandre wondered, okay, can I do that with Tangelo? Is this easy? What do I need to do? And it was pretty easy. He realized that, you know what, actually all of the tools I need are already in the toolboxes, right? So I should be able to easily draw my tools from these toolboxes, assemble my pipeline, and do what these guys did in the paper. And wow, that was very quick. The entire code, for example, is about 50 lines. The left part here, don't squint too hard, is really specifying your molecule, and Alexandre discovering how to play with graph with a package in Python for the first time. And all the chemistry is on the right part. That's it. He just grabbed the problem decomposition technique, paired with VQE, and he was able to reproduce results from this publication very quickly. He was actually able to go further because it was leveraging our VQE that is very complete, provides access to a lot of options and everything there. So how's a great example about how when you see a publication that's relevant to you, you can catch up fairly quickly and maybe even go further. Speaking of which, there's a series of work, still VQE related, very active field, that was done by a group. And I thought it's a very example of how we can really keep up with innovation here. For example, from VQE, this group of people developed an algorithm called DAVQE. Everything in orange that you can see on screen is actually a publication, an original work, right? And we find that a lot of the time, within 24 or 48 hours across, like, you know, a paper, we just read it and we can just implement or sometimes integrate it in Tangelo. From VQE to adapt VQE, it took just one file. And everything was built on top of VQE solver, which means that it comes with absolutely all its options. Suddenly, boom, we have a very rich adapt VQE. Then with an extra third line, boom, next publication, now we have qBit adapt, and we even support it with additional feature that we found was relevant to us. And then with only 14 lines in that specific case, suddenly, boom, what comes out from another publication, Tetris Adapt VQE, is also now part of Tangelo and available. So that's kind of the potential speed at which you can keep up with the state of the art that is advancing very quickly and moving it forward that we're talking about in practice for researchers. I'm not going to go too much in depth, but same with fault tolerant. We have many building blocks here, and to build essentially an application that can seem complex at first, well, you have all of the tools there, and that can really speed things up. And the last example that I find fun is that, okay, I have an entire algorithm library, but is it easy to just run my algorithm on a device? Like, you can see that through many different providers right now, they kind of just offer you only a few algorithms through their interface to run on the device they offer. But hey, I want to do good research with chemistry and quantum computing. I need to kind of, separate them to an extent. And the idea here is that you can define your very own compute backend. Here, for example, I play the game with IBM, where I say, I'm going to use my IBM connection object I showed you earlier, and I'm just going to define two methods: how to simulate a circuit, how to compute an expectation value. And now I can literally just plug it into one of the algorithms from the library. And most feature of the algorithm or the entire algorithm can run now on a quantum device. Whether or not you actually want to do that in the current state of quantum computing is another story. But this custom backend could be anything you wanted. It could be any code that does any kind of pre-processing, post-processing, and use whatever you want to do the actual computation. And that's the power here, is that really you combine all of these interesting algorithms and features for chemistry, but also great freedom, I think, in terms of quantum computing and the platforms you want to use and what you want to model. I'm going to go back and wrap up this presentation because I've been talking for long enough. One thing that I really want to highlight is that there's tremendous power in open source community. We've seen adoption by users in both chemistries, but also more from the side of quantum for Tangelo that find it interesting as a tool, as part of the ecosystem. Again, Tangelo is one tool among many. And if you want really to leverage breakthrough in quantum computing, we encourage you to use it in conjunction with all the tools that you think you need. There's some people from chemistry company that have been collaborating with us for years, researching these kind of problems. People that provide access to hardware that are interested in connecting us to their platform to help people do more chemistry on them. And there are people developing solutions around quantum computing, around different aspects of it, that are interested to see what Tangelo can do to help them solve tough problems. So the real question now is, what will you do with Tangelo? You can use it for educational purposes, you can use it for hackathon, but you can also keep up with the state of the art and push it forward with your research. Tangelo comes with a community, and well, it's a very interdisciplinary community. You're going to need a lot of help in order to take it to the finish line and do cool stuff. Software development, quantum physics, chemistry, quantum computing, or just, computer science. So whether you're a newcomer or an expert, you will find something interesting. You will manage to benefit from that. Finally, well, don't hesitate to reach out to Sandbox to explore avenues together if that is something you're interested in, whether they're quantum or not. Because the bottom line is quantum and quantum computers don't exist by themselves in a vacuum, right? You need to leverage the entire array of computational techniques and what we know from chemistry, from the problem, in order to explore what it can do for you. And that's it for my presentation. Thank you very much. I hope you have some questions for me.
Thank you so much, Valentin. I think you did a good job. You know, I think these talks are always a bit of a slog to get through, but I think the chat was engaged. I was engaged the whole time, and there were actually quite a bit of questions. So let's do our best to get through them all here. So there's quite a bit of interest. Mega Make on our Twitch channel had a lot of questions. Let's get to the first one. So they're wondering, can we put enough water molecules, for example, into a current generation quantum computer with Tangelo to see the actual properties matching macroscopic physics, or is that still out of range? I think I know the answer to that, but what do you think?
That's a really cool question. Let's go to this slide. You can see a little picture here in the biochemistry and QMMM. When you're trying to model such complex phenomenon, well, you know, the idea is that maybe the answer is not so much coming from the quantum computing side, but the kind of approximation of the kind of chemistry you're going to use. And for example, there are methods essentially that kind of approximate or put together all the interactions between a molecule and its environment. So maybe the right question is, should I put a bunch of molecules all together in a quantum computer in the first place? Can I approximate what my environment is doing through classical or from a quantum perspective, and then compute separately what it does with my molecule using the right algorithm? For this particular question, the example we have, for example, using a technique called QMMM that really approximates the interactions between the environment and the molecule. Maybe that's more promising than trying to squeeze a bunch of H2O molecules, which I think right now is out of reach for quantum computers. Hopefully that answers the question.
Yeah, I think so. Sorry, your username again, Mega Make, right? Mega Make. If that doesn't answer your question, I think Valentin will be on the Discord after, so feel free to poke a question there. There are some more questions here from Ketpunto. Hey, one problem I have had when trying to run VQE on real hardware is that it is very difficult to predict how much it will cost me because I don't know how long it will take to converge. So can you estimate with Tangelo the number of runs that will be necessary, or is there any like resource estimation built into Tangelo?
I think that's a very tough question. Even if we had the perfect simulators, I don't know myself how I would go about that. I think this is why it's very hard right now, because hardware, of course, are noisy, so you don't know where your convergence is going to take you. That is why I think we need to go beyond, for example, VQE, or try to think about utilizing quantum hardware a little bit better and researching this thing. Unfortunately, I don't have a problem. I think other packages, other people have researched that from a theoretical perspective a little bit better. I know that for now, in terms of VQE, we do not have such advanced functionality.
All right, cool. Another question from Dentucky Kirby on our Twitch. So Tangelo is open source. Is there capacity on your guys' end to deal with PRs from external contributors? Are there any issues, bugs, or features that are good to get started with if I wanted to contribute?
Absolutely, we'd love that actually. Like this is again a fully open source project. Absolutely anyone can come talk to us, suggest a feature. Like it's actually great because we developed this as an engine to accelerate R&D, our R&D, but by extension other people's R&D. But we don't know what interests you, right? We have a sense of that from what we see from the community. But if you want to study some particular problems, feel free to reach out, and even better, feel free to try to contribute this feature. We'll be there to guide you because we know Tangelo very well, and you probably know very well what you want to study. So yes, please go ahead. We'd love that.
Nice. Okay. Maybe one more question here from Andresu Lead. I think this is asked towards the end of your presentation. What is the chemical rationale, if there is one, behind fragmenting a quantum circuit derived from chemical calculations into smaller circuits? Does this fragmentation significantly impact the accuracy of the results?
Great. Again, I think this is really a chemical modeling question. All of these methods you see here have different approaches. For example, OpenShell DMET is like this iterative process that is good usually for strongly correlated system. Onium is going to be something that physically kind of breaks your molecule into different subsystems, cap the bonds, and then can treat them at different levels of accuracy. While QMMM is something that approximates the entire environment with, for example, a force field, and combine that with a high accuracy quantum algorithm on your molecule. Really, it depends on your system. It depends of the scale and the kind of chemistry you are looking at. I think that's what makes it challenging, and what makes the tools useful is that we're trying to equip you to kind of explore that and form an idea. But there's no guarantee. I'm not a chemist myself. People have a better answer than that, probably more insights. But as far as I know, it's the adventure we're exploring.
Cool. All right. Well, I think that'll do it. That's all we have time for right now. Again, Valentin will be on the Discord. So if a question you asked didn't get answered here, go to the Discord. We'll put the link in the Twitch chat for you guys to head over there. But for now, Valentin, we'll say goodbye. And j'espère que vous avez une bonne après-midi et une bonne soirée.
Merci. Merci, Essafi.
All right. Cheers. Bye.
Bye.
All righty. So we have one more talk coming up for today, everybody. So we have Karim from Qunasys coming up to talk about quantum chemistry, more quantum chemistry on quantum computers beyond VQE. So a very related topic, but stick around. That's our last talk for the day. We will be doing another giveaway in the chat on Twitch. So stay active in the chat, keep asking your questions, and you might win some swag. We will be right back. All right, we're back, everybody. It's the last talk of today. We're going to hear from Karim from Qunasys in just a second. Stay active in the chat. We will be having a giveaway after Karim's talk to end the day. If you win, you will get some swag. We'll contact you. We'll get to that in a second. But let's welcome in Karim. He's from Qunasys, but Karim is a researcher working on quantum algorithms for chemistry and material science with a background in theoretical physics. Karim, welcome. How's it going?
Yeah, thanks, Isaac. Good. How are you?
I'm dandy. It's been a long day, but sorry,
yeah.
Go ahead.
Yeah, please go ahead. Yeah.
Oh yeah, no, it's been a long day, but
because I didn't see it earlier.
yeah, it's been a long day, but we're here to put the cherry on the top. So the floor is yours.
Yeah, thanks. So I'm Karim Essafi working at Qunasys. So I'm going to tell you about quantum chemistry algorithms on quantum computers that go beyond VQE. So just for a little recap, so Qunasys is a quantum computing startup based in Tokyo in Japan. So it was founded in 2018 by our CEO, Tenin Yan. And we have some advisors at the Osaka University, including Professor Keisuke Fuji, who is a big professor in quantum information. We have about 50 employees, with half of them having a PhD either in physics or in chemistry. And we develop algorithms and software for quantum chemistry using quantum computers. So our focus today is going to be on quantum chemistry. So just as a small recap, so in quantum chemistry, the wave functions contains all the information about the electrons of a given molecule. This information can be used to compute the different properties of the molecules, such as energy or the structure or the reactivity. However, this computation can be very challenging because of the complexity of the electron structure. Even if the molecules can seem small, like it's still very complex problems. And we can solve some of them using quantum computers if the molecule is small, but as soon as we get bigger and bigger molecules, that becomes very challenging, both for classical computation and for quantum. So the algorithm has been used a lot in quantum computers is the variation quantum eigensolver. So this is a hybrid quantum classical algorithm for minimizing the expectation values of some parameterized circuits. And here you have a schematic view of how this algorithm works. So first you define your fermionic Hamiltonian and your Hartree-Fock wave function. Then you map this into qubits, and then you find an ansatz that you want to minimize with some parameters theta. And then you send this to your quantum computer where you do the preparation of the trial states, and then you do some measurements. You feed that measurement to your classical computer for the optimization, and then you feed back the results back to the quantum computers, and you go back and forth like this until you reach some converged results that minimizes the ground state energy, for example. So the applications of VQE are quite wide, going from you can use it to do molecular dynamics, photochemistry, but also for solid state materials as well, to calculate, for example, the band structures of a given material. However, the issue with VQE is that it requires a lot of resources in terms of number of qubits to deal with the noisy circuits that we have. And the problem is that the current hardware has, like the quantum computing resources are very scarce, meaning that we have a low number of qubits and the gate fidelity is still relatively low to be able to do VQE for large molecules. So one would need to find techniques that reduces the required number of resources. And that means like reducing the number of qubits, having shallower circuit depths, while still having a high performance so we can tackle more challenging problems. So how do we reduce this? We can either develop a more efficient algorithm that requires fewer resources to reach the chemical accuracy. We can use symmetries of the systems at hand, and we can also use some quantum embedding methods, for example, where we divide the system into two parts, where it's one high level and one low level method, depending on the part that we are tackling. So at Qunasys, we focus a lot on research. And in our research, we have developed different ways of either improving VQE algorithms or going beyond VQE, which we're going to be talking about today. And also, we also have some stuff on fault-tolerant quantum computing. So today, I'm going to mainly be talking about grouping via finite projective planes and the quantum selective configuration interaction, or QSCI for short, and an adaptive version of it called Adapt QSCI. So this at QSCI, we published or we submitted papers to arXiv last year. And the idea behind this is that the ground state energy on a noisy device can sometimes not, like the results that we get using VQE can sometimes not be variational. What I mean by this is that even if the VQE is technically a variational algorithm, it means that it should respect the variational principle. In practice, when you run this on an actual device, you have either statistical noise or physical noise on the device that can lead to measurement errors, and those measurement errors can lead that you violate the variation principle, which means that you can find ground state energies that are actually lower than the real exact energy that you would get if you knew how to do the exact computations. And you can see this already in this graph here, where some of these stars are below the exact value, which is the red lines. So to overcome this challenge, we want to develop an algorithm where a low value of the energy still respects the variational principle, and at the same time reduce the quantum resources required to do this. And this is where QSCI comes into play. So here we have an overview of how this algorithm works. So we start with some input states, which are called psi in. And then we measure the states in the computational basis on a quantum computer. And then we do a sampling, which means that we're going to select the configurations that appear the most. And then using these configurations, we're going to reconstruct our Hamiltonian on a classical computer in a subspace, and then diagonalize this Hamiltonian in that subspace. And by doing this diagonalization is done classically, so it doesn't require any more quantum resources besides the sampling phase. And on top of that, the ground state energy that you would get, because it's an exact diagonalization on a classical computer, you don't have the hardware noise that comes from quantum devices. And also, we know how to do exact diagonalizations for quite large systems on a classical computer. And by doing that, the energy that you would get will be exactly that subspace, and you will obey the variation principle. And I'll show you some of these results. So here is QSCI, where we start with VQE as our input states. We have run this simulation on a noiseless simulator, and this was done for a water molecule using 10 qubits. And looking at the different results, so the colors correspond to different sizes of the subspace. So R defines how many configurations we have selected for our subspace. And you can see that already at R16, which is this orange line, we are already at the chemical accuracy. So here the y-axis corresponds to the energy difference between the one we get from QSCI or VQE minus the exact energy that we would get using CASCI or FCI. And you can see that QSCI with a subspace equal to 16 has already reached chemical accuracy, and it gives us results that are lower than what you get for using VQE. And for comparison, using a classical method, if you use a CASCI for this problem, you would need about 100 Slater determinants. So this is doing exactionization on a subspace of R equals 16 is actually easier and faster to do than you have to do our CASCI calculations. So you can see that this is already showing some promising results. And then we also run this on a linear chain, H4 molecule using 8 qubits. And this was run on the INQ device. So this was run directly on a noisy computer. And the different lines that you see on the graph corresponds to the different iterations. The color corresponds to the size of the subspace. So yellow is R equal 1 and orange is the same as before, R equals 16. And the lines with a marker corresponds to an average of different runs at that subspace size. And one interesting fact you can see here is that some of the runs actually perform better than using CISD, which is the configuration interaction with the single and double excitations. So some of these can have better accuracy than on a classical computer. And in general, if we take the averages, we get better performance than doing VQE, for example. Which means that we could get higher accuracy using fewer iterations than we do using VQE calculations. And to see how this method, if this is scalable, because we're interested in larger molecules, so we did simulations to extrapolate what this would look like if we had access to 50 qubits. And we tested this on the CR2 molecule with varying different sizes of active space. So here we have the we look at the resources both on the classical and the quantum side. Also on the classical side, this is not very demanding, so the scalability will be just fine. And you can see that if we wanted to run this problem for 50 qubits, we would need about 10 to the power 3, which is like 1,000 Rs, which is thousands like size of our subspace. And we know that this is not a problem because we can run up to 10 to the power 7 on a supercomputer. And looking at the on the quantum resources required, basically, if we had access to a 50 qubit device, we could do all the sampling within 1 day for this specific molecule. So you could say like in about 2 days, you could get very good results between doing the sampling and then doing the exact diagonalization on a classical computer. So in summary, this method is very promising because one, it obeys variation principle, requires fewer resources than the standard VQE, and also you can run this with shallower circuits. But of course, at this level, we were still using VQE as our input state. So future direction will be to use a different method for the state preparation, and also to apply this to test this on bigger molecules to have a better demonstration of the quantum advantage that you would get from this approach. So this first thing is what we have already done, and that's my next couple of slides are going to be about adapt QSCI and how this works. So this was also published late last year. So the idea of adapt QSCI is to use an adaptive construction of the input states in which that we run the QSCI algorithms multiple times and we grow the input state iteratively. So this is a similar idea to adapt VQE, for those who know adapt VQE, and I will tell you a little bit about what's the key advantages of adapt QSCI compared to adapt VQE. So at the first step, you define a pool of operators that are the generators of rotation gates, and you put this in a pool, and then you also choose initial input states. An example of these operators could be a single or double excitations of electrons. So this is the similar things that you would do if you're using adapt VQE. And then you perform a QSCI on the input states that you have chosen at the step K. This will generate your R-dimensional subspace, then which you use to construct the effective Hamiltonian, and the smallest eigenvalue and the associated eigenvectors are EK and CK. And then you use this CK to do an evaluation of this quantity H, which is basically the expectation value of the commutator of the Hamiltonian with these operators P. And then you choose the operator in the pool with the largest value of H, so in absolute values, and you denote it as PTK. And then you use that operator to construct the next step, step of your input state, and with some parameter theta k. And you minimize this this function here to find the optimal value of theta k that we denote as theta star, and then we inject that into the input state phi k plus 1, so at step k plus 1. And as I was saying, the theta star is the one that we get from this minimization here. So your new input state is the one given here. And there's several key advantages of doing this. So one advantage is that you only need a quantum computer for step 2, so to perform the QSCI generation of the R-dimensional subspace. You need fewer number of measurements compared to adapt VQE, which means that you would require fewer quantum resources. And the parameters theta do not change from one iteration to the next. So which means that if I find my theta star 0, then when I move to step k equal 1, that value of theta star 0 remains the same, and I just need to optimize to find theta 1, the optimized value of theta 1. Whereas in adapt VQE, at each step, you have to re-optimize all the parameters, which makes it much more resource intensive and time consuming as well. So here are some of the results comparing adapt QSCI and adapt VQE. And what we have seen is that, so this was run on a H4 and H6 chains. And we see that we require fewer C0 gates to create our state phi k. to get a more accurate results than we would need than we get if you're using AdaptVQE. And you can see this in this graph where the blue dots correspond to what we get from AdaptQSCI, whereas the red line is the one from AdaptVQE. And you see that you need more numbers of CNOT gates for both systems. And if you look at the number of charts, we see that AdaptQSCI was requiring 10 to the power 6 for H4 and 10 to the power 8 for H6 to get to reach chemical accuracy, whereas for VQE, the lowest number of shots that you would need to get the to reach chemical accuracy as well is a magnitude bigger for H4 and like 2 to 3 times bigger for H6. And this is like basically a lower bound. So the actual resource number of shots that you require is actually much bigger for AdaptVQE than you would get from AdaptQSCI. So this is a very promising method to use for NISQ devices that would allow us to tackle bigger molecules. And on top of that, the next direction that we need to do is to extend this algorithm to excited states calculations. And I think I still have 1 more minute or 2, I guess. So I might jump over this part and just tell you directly about the software we've been working on, Curie and QReparse, and I'm just going to be talking about QReparse here, because I think it's more relevant for QHack. So this is a Python library that we developed that is very modular, which means that you can use the modules that we have it and combine it with your own algorithms or your own modules that come from either other libraries, and you can run it on different platforms, either on a simulator using QLAX or STIM, or also on real devices via Amazon Braket or IBM Qiskit. And there was a lot of focus on high performance, and here we compare QReparse in orange with PitCat and Penny Lane, and you see that at least for lower, small number of qubits, QReparse is performing better, and they basically perform similar at when the number of qubits increases. And if you want to test this library, we have some ready-made tutorials that you can access going to this link. And we have different types of tutorials, either to estimate expectation values, doing sampling, you having noisy simulations, or even error mitigations and other stuff that you can have look into. So thank you for your attention. And if you want to reach me, you can either reach me on the Discord channel or via my email. And here's a QR code where you can access all of our papers at Qunasys. Thank you.
All right, Karim, thank you so much. I'll leave this slide up here for those who want to see your email and scan that QR code. Yeah, thanks so much. That was super interesting, actually.
Thank you.
Let's get into some questions. We actually do have quite a few here. So we have Chengling_X0 on our Twitch asking, is QSCI outperforming classical select CI?
Good question. Is it outperforming it? So at least at the level we have now, we show that it has similar performance, at least for smaller molecules. Let's see. I don't have the, yeah. So here, of course, we only can test this because we don't have access to bigger quantum computers. For these small molecules, it has similar performance, but with fewer number of resources. I was saying that, so QCI is a classical CI, and you see that for this one, you would be diagonalizing a system with 100 slated determinants, whereas using QSCI, you can do this with 16 basically dimensional matrix. Well, 16. I would say states in your subspace.
Okay. All right. Okay. So Chengling, hopefully that answers your question.
And here it compares also with CISD, which is also another configuration interaction with single and double, which is also a classical method for this. So.
All right. Okay. Nice. A question from Kentucky Kirby. On one of your slides, I can't remember which one. There was you showed some results for chromium-2. Kentucky Kirby just said chromium-2 interesting choice. Why?
Oh, because this was like a complex molecule to work on. That was complex enough that it was interesting, and small enough that that would be like a goal of like I would say medium term goal to be able to do this one, and was a very, I would say, in some ways trivial one to make the resource estimation for in a easy and clear way.
Right. Okay. One last question here from Andresi Lead. I'm not entirely clear on the role of a quantum computer in implementing the method utilized by QSCI. Generally, is this computation carried out classically?
It's both. It's a hybrid algorithm. So you here at the input stage. So this part is quantum computer, and this part is classical computer. So what you do in the quantum computer, you do the sampling. So you prepare your input stage, you do a sampling. The sampling will tell you, when you do sampling, you have such a number of configurations that will appear, and you will select those that appear the most. And those that appear the most, you use afterwards on a classical computer. You feed that to a classical computer to construct your subspace and do your effective Hamiltonian diagonalization over there.
Right. Okay. All right. Well, there was a couple more questions, but if you want to ask them on the Discord, that's the place to do it now. For now, we have to say goodbye. Thank you so much, Karim. Karim, this is your second QHack, or is it your third?
Yeah, nice second.
Second, right. Okay, so Karim's, I think actually, Karim, your previous QHack talk is on the Xanadu YouTube channel. So if you guys do want to go check that out, a throwback to last year, this one will be up on the Penny Lane YouTube channel right when the stream ends. So if you want to watch that back, you can. All these are being recorded. They're all on our live, or they're all being recorded live right onto our YouTube channel. So yeah, watch them back at your leisure. Karim, it was a pleasure to have you again at QHack. Hopefully we can have you back next year. Have a great rest of your day.
I hope so too. Thanks, Isaac.
All right, cheers.
Have a nice day. Cheers.
Okay, so that wraps up day number 1 of the sponsor demos. Let's check out next day's schedule, which is tomorrow, February 16th. Again, be active in the chat. We're going to do a giveaway shortly after here to see who can win some swag. Yeah, tomorrow we got a big lineup. Let me just pull it up here, the full thing. Right. Okay, so in the morning, we have Leonardo from Entropica. Then we have an hour-long demo from 2 folks at Haiku. Then we have Multiverse Computing. And we have a demo from Rolls-Royce. Jarrett Smalley is going to join us. In the afternoon, we have a quick coffee break after that. But in the afternoon, we have the second talk from NVIDIA, so how to get started with CUDA Quantum. And then we have a bunch of other stuff, Alice and Bob, IonQ, another 2 AWS demos, and a demo from Q-Control. So a jam-packed, action-filled day. I want to give another shout out to our sponsors, some of which who have presented and will be presenting tomorrow. Thank you so much for your time spent putting into QHack, and it really does make this event that much better. So we really do appreciate everything that you do. I do actually want to also go onto qhack.ai. It's been a hot minute since I was last on there, so let's go there. Right, so the Open Hackathon will be beginning tomorrow. I can't remember the exact time, but my moderators in the chat will put the exact time in the chat if you're wondering. So when it does become live, you want to go to this tab right here. Yeah, you want to go to this tab right here. There'll be categories for you to choose, like a topic. I mean, it's still open-ended, right? But there's, like, I guess, categories for you to get started with and kind of contain your answer within. Those will be done. You have to submit your project to the QHack portal. There will be like a place to submit your project right here. We're not doing like a GitHub PR anymore. All of it will be done right here. You can still submit like a GitHub repository and stuff like that. It should be obvious in the instructions on this tab when that becomes active. You have to submit that on February 22nd by 5 p.m. Eastern, I believe. There's also going to be 2 rounds of power-ups that we'll be awarding to folks. Part 1 of the power-ups will be to do with how you do in the coding challenge. I believe it's the top 15 teams in the coding challenges will be getting a power-up. So it looks like the top 15 is still up for grabs. Again, the coding challenges will stop tomorrow at, let me just check here. Coding challenges close tomorrow at 5 p.m. But I think we grab the top 15 a little earlier than that just to make sure that we get in contact with people. So keep chugging away at the coding challenges. Let me see here. I think we have a handful of teams that have completed all the challenges. Oh, wow. 6, 7, 8 teams so far that have completed all of the coding challenges. Definitely less than last year, but still quite amazing that all of you have completed that all of the questions. I'm actually kind of a little baffled. If you want to know what prizes you can win for the Open Hackathon, go to the prizes tab here. For the coding challenges, there's a $35,000 prize pool, so that's being eaten up already, I think, by the people who have finished all the coding challenges. We have the Open Hackathon prizes as well. Big prize pool there. Again, lots of power-ups to be had to make your project even better. Definitely go to qhack.ai for all the stuff that you need for information there. Again, you can find the full schedule on qhack.ai as well. So this was today, tomorrow. There's a bunch of talks coming, quite a bit. Browse through that at your leisure. Okay, I've talked enough. Let's hear about this giveaway. So let's go to the giveaway tab. That will allow me to do a giveaway. Okay, so let's see here. Everybody, be active in the chat. You may win something. I'll leave it open for 5 more seconds. 5, 4, 3, 2, 1. And Dressu Lead, congrats. You have won the giveaway. Thank you. You did actually ask a lot of questions throughout the day, so well deserved. One of our moderators will get in touch with you. If you have Don't Take Whispers from Strangers turned on in your Twitch settings, make sure to turn that off so that one of our moderators can contact you. We'll get your information, and we'll set you up with some swag shortly after QHack. All right. Let me put up the next day's schedule one more time here for you to look at. Thank you so much for joining us today. Really, really do appreciate everybody participating, asking questions. It really means a lot. Yeah, let's just end it there. I've been Isaac. You've been wonderful. You could have been anywhere in the world, but you chose to be right here today, so we really appreciate that. Have a great rest of your day, afternoon, evening, wherever you are, and we will see you tomorrow at 10 a.m. Eastern Time for more awesome talks. Take care. Cheers.